Okay, let me double check again. The first author's paper, VGG, SLAM is here. Yeah, I didn't see him online as well. Yeah, anyway, let's get started. And I think the Zoom is right now recording. Yeah, it's sharing. Let's see. Yeah, it's recording. Okay, good. Yeah. Welcome to the nice visual odometry workshop and as well as computer vision applications based on location clues. This is organized by myself and which I'm Guoyu Lu and with Friedrich Friendorfer and currently cannot come here because of the conflict of ACRA, and Yan Yan and Nipu Sebe is here and China Hamedu, he's the general chair, so he's not able to come here right now. So first of all, why we want to do visual odometry and location based on applications, quite a lot of applications. For example, in robotics, if you want to do any actions, you need to really have the information about the location, and you want to know the motion and the estimation as well. And so that is one thing. And also in augmented reality, if you want to augment graphics accurately, and you need to first know where you are. And so you want to know where you want to augment these graphics precisely. So that is also an application. So in autonomous driving and odometry and mapping, that is also quite a lot of applications. And so also in navigation, and sometimes you want to work on depth estimation, depth ranging. So you want to know how far is it away of the objects. So that is also some applications you want to use actually for visual odometry as well. And I don't know you guys, and when I take Uber, and quite often they ask me for the location, and based on the location, they provide quite a lot of services, and those location-based services, and you can also use computer vision to help you to provide this kind of, no matter what kind of services you want, actually. And beyond of the traditional robotics, augmented reality, autonomous driving application, for example, in indoor environment, you can also use those kind of images as well as computer vision and techniques to help you to navigate inside of indoor environment, as well as, for example, in agriculture, and you want to navigate your robotics drones, and in civil engineering and autonomous driving, which we just mentioned, even in medical imaging, and you want to do surgery, and actually sometimes you have the camera mounted on the CRISPR, and quite often you also need to know, okay, where you are inside the human body. Okay, and that is why we organize this workshop. And specifically for this series of workshop is already organized actually in 10 years. This is nice edition, but at the same time in the middle, we have a merged edition. So it's nice right now. And in this time, we have 5 speakers as well as 4 oral papers. The workshop scope and is actually quite broad, and that can come from visual odometry, SLAM, scene understanding, and to location-based services, for example, GPS denied environment, and how to do navigation, how to do the localization, as well as some other special cameras, for example, thermal camera, multi-spectral camera, event camera, and multimodal sensing, and applications like nerve Gaussian splitting, and with different applications, autonomous driving, UAV perception, as well as field robotics, no matter that is the medical field or the agriculture field. And so this program is starting right away, right now, and lasts until 12:50. And there are 5 keynote talks and 4 oral presentations, and oral presentation will be limited to 10 minutes, and keynote talks will be 40 minutes. Okay, and at the same time, and quite a lot of people are sitting inside of the room, and we have Zoom link and for the people who registered for the virtual participants. And for those who didn't really participate as a CVPR inside CVPR, who didn't register, we also provided a YouTube link actually. And so if you know anybody who is interested and who didn't register CVPR, feel free to tell them we have YouTube live stream right now. It's happening right now, and they can still listen to all the talks as well as ask questions. Okay, and this list of keynote speakers, and we will introduce them each and during their talks. And the first one is actually VGG The first 4 is actually oral papers, each 10 minutes. And after that, will be keynote talks, and starting from 9:30 and until 12:50. So that is why first we want to introduce the first paper, VGG SLAM++. I still want to double check whether the author is here or whether the author is online. Okay.
Hi.
Hi.
So yeah, I'm online.
Okay. Okay, you're online. So can you try to share your screen?
Sure.
Yeah. I will stop sharing.
You can hear me well, right?
Yeah, I need to try see how to allow okay, give me a second. Can you try to speak?
Hello.
No, audience cannot hear. Let me check.
In any case, I hear very well, Avilash. I'm online also, okay? I hear very well.
Yeah. Hello. Am I audible?
I think the problem, Avilash, is their side. Okay, I think we can hear you well.
So when they talk online and they couldn't hear actually.
Okay, so they can't hear online.
Hello, can you speak?
Hello.
Yeah, it's
Hello.
very small. They cannot hear.
You're not connected.
Can you see my screen?
We can see your screen, but we couldn't hear your voice for the audience.
I see.
You have to wait till this turns on.
Okay, should I plug out? Or?
No, keep it
No,
plugged in.
okay.
Do you have they don't have it.
It seems this one is connected to here.
You have an aux?
No. Okay.
Go to your settings,
Okay.
your sound settings.
Okay. Voice, right?
You mean my settings?
Okay.
There you go.
Yeah, okay. It's right now it works. Okay, you can go ahead to present.
I'm audible right now.
Yeah, yeah.
Oh, okay. Hi, so I'm Abhilasha and I'm going to present my paper, VGGT SLAM++. So the timeline overview is like VGGT, which came in CVPR 2025, followed by VGGT SLAM, which is a SLAM approach built atop VGGT in NeurIPS 2025. And now we have VGGT SLAM++, which is essentially a drift corrective backend added for the long trajectory drifts in SLAM problems. So VGGT can consume only 60 frames per batch with an RTX 4090 GPU for the accurate structure from motion solution. And hence this feed-forward neural network cannot be extended implicitly as a SLAM framework, which works with tens of thousands of RGB frames as input, unless we explicitly solve for these poses across subsequent batches.
1 second. Your slide seems like freeze already. Somehow.
Oh,
I don't know.
which slide can you see right now?
Let's see. Right now, it seems like
See.
can you reshare your screen again?
Okay, sure. Can you see the screen right now?
We can see your screen. You can share. Try to share and.
Right now?
Yeah. Now you can go ahead. Yeah.
Sure. Okay.
Yeah, you can continue.
Sure. Okay, so VGGT SLAM solves this memory inefficiency problem in vanilla VGGT by solving these inter-batch poses using a homography matrix for the overlapping frames across the batches, which we also call submap. But there lies a caveat that these homography solutions can accumulate the noise or the trajectory drift, especially while talking about long trajectories, say greater than 500 meters path. So VGGT SLAM++ solves this drift accumulation problem by storing a compact fingerprint of the global environment in the form of a height map, which we call a digital elevation map or DEM, to correct the local camera pose prediction. So as you can see in the top row of this image, we have the drifted trajectory, which is from the VGGT SLAM vanilla pipeline. And in the bottom row is our corrected trajectory, which is stabilized by the backend module, which is our novelty in VGGT SLAM++. So we cut off the drift at a high cadence with our backend. So coming to the pipeline of VGGT SLAM++, we have three components: the front end, the co-visibility graph, and the SLAM backend, which run in parallel. The front end is a chunking of the RGB frames in small batches or submaps, which is input to VGGT to obtain the camera poses per batch, which is aligned to a unanimous point cloud using a similarity 3 manifold solution. And this aligned point cloud is rendered to a global DEM or digital elevation map fingerprint structure of the global environment. This DEM is patched into smaller tiles, and this tile is input into DynoV2 to obtain an embedding of that tile. This embedding serves as a graph node of my co-visibility graph. This graph is rendered using the FAISS, F-A-I-S-S, which helps in cutting off the time complexity to a logarithmic n function, which is very essential in SLAM problems having tens of thousands of frames. Now, when a new submap query arrives, it queries my retrieval gallery, which is augmented in the form of a graph. And the graph returns the best possible submap searches, which can be a candidate loop detection. Now, this candidate loop detection are further verified with a global with a VPR or a place recognition module. For my case, I use AnyLock, and this verified submap matches or the loop detections is a loop edge. Once an edge is identified, I pass it through an optimizer. In my case, I use the GTSAM. And again, a solution in the similarity 3 manifold helps me in getting the corrected poses, and the odometry drift is removed, and we get the corrected global DEM representation too, and this goes on and on, runs in parallel, at a 2 FPS speed. The front end goes in parallel at a 16 FPS speed. So I would like to demonstrate this with the Kitty 05 dataset without a spatial corrective backend on the left and with a spatial corrective backend as the novelty in VGGT SLAM++ on the right. So coming to the power in the fingerprint that we have used, the DEMs, they preserve a quite accurate structural information as proven by running an object detector, predicting the teddy, the chessboard, or the parked vehicle accurately in 3 established dataset scenes from the TUM, from the 7 scenes, and from the virtual kitty. As you can see, the bounding boxes and the labels probably the teddy, chessboard, and the parked vehicle. So this is a representation about how the camera frustrums, when plotted in the trajectories, look on top of the 3D reconstruction from VGGT. So we have some custom datasets as in part A and D, and parts E and F are from established datasets like the TUM. So compared to VGGT SLAM baseline, we achieve an overall improvement in the ATE RMSE in meters with 18.6% improvement averaged over 5 datasets. Thank you. That's it. Any questions? I'd love to answer.
Maybe we have time for one question. Okay. So thank you very much. So let's say the next speaker is here, right, Henry?
Sure.
You're the second one, right? I remember you are the second one. So scars. Let me check. Yeah. Yes, scars. SCAR. Yeah. Yeah. I think yours is yours. Yeah. I think you are the second one.
Okay. Great. How do you want to do it? So I have to do a USB stick or
You need to log into.
Okay.
So to the third speaker here, third our talk and the RF log.
Yes, I'm here online.
Okay, cool.
Good to go? Cool. Great. So my name is Henry. I'm with the Framework Institute, and today I want to present you SCAR, which is a technique for cellular-based, imagery-based calibration for aerial recordings. And to give you the motivation why we're doing this, so typically we are working with visual inertial navigation, so GNSS denied navigation. And for that, we have a visual inertial platform, so with an ultralight, but also with grounds. And our typical route on this is that we do offline calibration. So for example, with large calibration targets from Calibre or other companies or other techniques. And then we do our measurement campaigns, for example, 10 days later or 3 months later. And then we see that we got into problems. And this is because if we calibrate our system on the ground, we have a different lever arm compared to when we are in the air. And especially over different measurement campaigns over time, we see that the calibration is changing. So the sensor mounts getting skewed, or there are differences in the mounting, and then we have problems with the calibration. So you can see here on the bottom right, for example, if we fly 3 months later, we see that if we project non-ground control points into the image, we see that we have a large calibration offset than compared to in the beginning. But still, if we are near to the calibration, we have offsets because of the environment, because of the big lever arm. And we attack this. So the core idea is that we use the satellite images to refine the calibration when we are flying. And the core idea I want to shortly present. So when we are flying, for example, we have an image, that's our camera footprint. We take our satellite or our UAV image, so that's on the left. And then we have the satellite image on the right, so we can render it based on the current camera pose that we predict. And we can do image matching. So we did a lot of extensive checking for which image matching between aerial and satellite is going well. So don't have time to go deep in that, but that's in the paper. So we do image or aerial to satellite matching, and then we track these matches of the known georeference pixel in the image. And we do that to refine these calibrations, so to correct this offset, which is static, so a static calibration offset correction. And we do not need special calibration maneuvers, for example, like as we do on the ground, so don't fly extensive curves or something like that. And how do we do it? So we create our automatic ground control points by this georeferencing. And then we also have an initial guess for the calibrations. And we have posters of an onboard INS. And we do a factor graph optimization by using post-prior. So from the INS, we have our 3D anchors. We can estimate the accuracy and the spread of these anchors for the pixel estimates. And we have the reprojection constraints, and we optimize the camera poses. And after that, in the end, we can refine or extract our extrinsics from that by estimating the best extrinsic between the INS and the camera, and also refining the camera calibration in the flight. And we do this in a staged optimization, so that we first correct the rotation, then the translation, to don't end up in bad minimas in the optimization. And we work really closely on real-world data. So we have a platform, as you can see here, so it's robotics related. And this platform we are flying with our ultralight, you can see on the lower right. And then we use the actual autophotos or satellite data for creating our references for the georeferencing of the pixels. And we created or set up some sequences of our flights. So 2 for training, 2 for validation. And we did our testings on that. So we, for example, refined the calibration on the training ones and validated these validation ones, and this over the different time spans. So for example, from 2022 to 2024, when the calibration is in 2022, so close and distant to the initial calibration. And we see what the outcome of SCAR is. So when we are, for example, distant to the initial calibration, we see, so in yellow, that's the reference of caliber on the ground. And we also did experiments with lens mono and so the SLAM system, and also with Colmet to refine it. And we see that these are lowered, so the reprojection error of the ground control points, but we see it's still high. And when we use SCAR, we see that it's getting lower, especially when we optimize both, so the intrinsics and the extrinsics between both sensors. And when we're close to the reference, we still see that there is an improvement, yet it's not that big when we compare to the distant setup. And we also did a task-based evaluation, so for visual localization, and we see that the rotation error for zero-shot visual localization in these settings is getting better in all cases, even when we are very close to the initial calibration. And in the end, I want to give you some qualitative results for this. So on the left, you can see it's a bit low frame rate, but nevertheless, on the left, you can see, for example, the median reprojection error in the initial case. You can see that that there is a constant offset to the left. So, for example, the pitch offset, and you can see this is corrected very nicely on the right. So with a better median reprojection error for the images, it's still somehow in some cases bigger when through curves and something like that. But you can see that these reprojections are very close to the real points in the world. It still has limitations. We have the assumptions for the accurate poses here, and we also depend on reliable aerial to satellite matching, which we're still working on, but these are, as of now, limitations of our scenario. And with that, I want to thank you, and I'm open to answer any questions.
Okay.
The satellite downstream, what kind of resolution do you need from the satellite? And how clear do you need that capture? Are you working with like annual mosaic or trying to find just a really clean image?
That's a very good question. So we try different resolutions. So it really depends. So you can calculate the resolution based on the altitude. So when you fly higher, you need a less good resolution. It also depends on the camera resolution. So what we did in our experiments, we tried to simulate the real resolution we have in the camera footprint. So for example, like 5 pixels per meter. So this is a rough estimate. And in general, we also did, clean images is a good one, but rather in urban imageries, there are a lot of edges and other features we can detect well. So this is rather the major points of urban and rural. Urban is definitely better for matching use. Thank you.
Yeah, also the distortions and the solving mechanics. Also, work back to where your response from state this the identifier this capture state this you explain that.
It's a good question. So first of all, the distortions, we optimized them as well. So we didn't see that in our case, at least, there were no very beneficial optimization there, but they, in fact, in the vectograph optimization can be optimized. And in these cases, we are flying 300 to 500 meters above ground. And I would suppose if you're in a close range, so not going from 300 to 4 kilometers, okay, this is a different scenario. So, but if you are in a similar range, you don't need to recalibrate this every time. It really depends on the temporal range, I have to say.
No further questions. Thank you very much, Henry. Now let's see the third speaker, the third oral talk. Can you share the screen?
Yes. Okay, can you see my screen?
You can go ahead.
Okay, so everything is visible. Hello?
You can begin.
Okay, great. So, greetings from Budapest.
I
Unfortunately,
couldn't
we
hear
were
you
not...
right now.
1, 2. Hello?
Yeah, now we can hear you. Yeah.
Okay, great. So, greetings from Budapest. Unfortunately, we were not able to attend CVPR this year, but we are very excited to show our work, RF-LOC, which is a robust visual radio frequency-based localization in large-scale environments. So, precise 6 degree of freedom localization is fundamental for a lot of different tasks, such as augmented reality, the metaverse, robotics, and so on. And we define localization as finding the rotational and translational correspondence between two coordinate frames. A typical situation is that one coordinate frame belongs to the camera, the other one belongs to the localization map, and then we want to find the pose between these two. The process usually is quite straightforward. In single image cases, we find features on the image. We want to match these features with the features that are available on the map. These are done by some different feature representation or descriptors. And if we can do this kind of feature extraction and matching in a reliable way, then we can have a good estimate of the pose. Unfortunately, visual-only localization is very, very challenging. Single image visual pipelines lack the necessary spatial context in situations like repetitive textures or homogeneous surfaces or low lighting condition. So in environments like warehouses or offices, this kind of problem becomes very challenging and difficult. So in order to improve robustness, we could apply different probabilistic filters, such as the particle filter. However, for large maps, quite easily the computation is becoming prohibitive, so it's not very useful. So we started to think, how can we tackle this problem from a different perspective, seeing that there are situations when single image-based methods are failing. So we said that, okay, if we cannot solve the problem with one image, let's collect a sequence of images. And during that trajectory, we could also record the radio frequency signals, the RSSI values coming from different access points. And as soon as we have a sequence of images, by using different SLAM algorithms, we could turn the images into point clouds that are describing the structure of that environment. So by having the 3D structure and by having this kind of spatial RF fingerprints that are tied to the trajectory, we try to fuse this kind of information together in order to create a more robust method that has also low computational cost. When we speak about the deployment scenario, we could say that we have the robotic agent or we have the AR headset. We can run some lightweight visual inertial SLAM to build the local structural maps and to collect the radio frequency measurements. And then we transmit this local map together with these RF measurements to some edge server. And on the edge server, we already have the pre-encoded global map that was recorded offline by different sensor modalities like LiDARs, cameras, and so on. But here it is very important to know that after we train our localization model, then the massive global structure and RF features are already encoded and cached offline. So there is no need to rerun the encoders on the global map. This is how we can achieve almost near real-time localization performance. So we think that structure and RF are the keys to robustness. And we say that because in case of, if we can, let's say, find correspondence between geometrical structures of the local and global map, we can provide centimeter level precision. But if we have this kind of repetitive environments, then hallways that look identical, then we can get easily lost. But then if we have the radio frequency data, the RSSI fingerprints, then we can create a unique and absolute room scale fingerprints. here it's important to know that RF alone cannot give very accurate precision, but it can provide the global context that it's needed to eliminate the spatial ambiguity. So this is why we think that mixing structure with RF signals, these are quite complementary signals and can work together in order to get a more accurate solution. So here you can see the architecture of the RF lock. The two sides are very similar. So here we have on the left side we have the global structural map and the global RF map. On the right side we have the local structures. These point clouds practically enter in different encoders. We have a structural encoder and we have the RF encoder. And since these are very heavy point clouds, we need to reduce the number of points. So by using voxel subsampling, we can define a coarser output. And then the task of these encoders is to create appropriate feature representation for this coarse structural and RF superpoints. So after we have the feature representation for the superpoints, the next step is the fusion. We are using different transformer fusion architectures in order to exchange information between the structural descriptors and the RF descriptors. This is how we can improve the discriminativeness of these feature points. And after the fusion, we can start the traditional process of finding point correspondences between the coarse points of the global map and between the coarse points of the local map. Here we used the method presented in the geometric transformer paper. After we have the corresponding point pairs, we extract the fine superpoint patches coming from the global and the local decoder. Once again, we want to find correspondences between these fine points, and then we do post-estimation. So these are the main blocks. So now let me give you a more detailed description about this. So in case of the structural encoding, we have the global map and the local map. And as I said, we are using voxel grid-based subsampling in order to reduce the number of points. Here we use two different levels, the coarse level and the fine level. And the task of the backbone, which is a KP-conv-based backbone, is to create the appropriate representation for the feature points. And here are two maybe novelties that we can share. So we also prepared two different heads that are tied to this backbone. The first is the gated superpoint repositioning head. So instead of anchoring features to arbitrary voxel grid centers, the network learns a bounded correction to shift superpoints to true geometrically stable features. This is important because if you just average out the points that are in one voxel, you are not going to get really good feature representations. The other one is the confidence regression head. So for every superpoint, we are going to regress the confidence. This is very important because this way the network is going to learn to downweight ambiguous flat walls, for example, and upweight distinctive structural anchors. For the RF fingerprint encoding, we couldn't use the KP-conv backbone, so we had to design a completely new encoder for that. It was not working with the KP-conv. So here in this case, we have as inputs a lot of fingerprint vectors. You can think about these fingerprint vectors as high-dimensional vectors having RSSI values coming from different access points. It's important to know that these are very, very sparse vectors. Usually, example, in the Lamar dataset, we have 200 access points, and we cannot measure, we cannot reach to every access points in all of the positions. So this is why it's sparse. Therefore, we had to introduce a binary mask. And we also found out that it's very important to use IDF type reweighting. So in case if one access points has a lot of different measurements in a wide or in a large area, that is not very useful from a localization point of view. But if an access point gives measurements in more restricted areas, that can be very, very helpful for localization. So we are applying this kind of reweighting. We are inputting into an MLB encoder. And after that, we define the RF superpoint centers. We find the neighbors of the superpoint centers. We are going to calculate RBF embeddings. This is how we create the tokens. And the tokens are going to enter in a multi-head attention architecture in order to create the final descriptor for the RF superpoints. The next step is the fusion. The trick is the same. So for every structural superpoint, we find the corresponding, or we find the neighboring RF points. We do some attention pooling, and then we can decide whether we have enough RF measurements around the RF point. If we have enough measurements, then we can proceed with the fusion. If not, then we are going to use a fallback mechanism, and we are going to rely solely on the structural information. So we cannot enhance the descriptor with information coming from the RF superpoints. And as the final step, this is very common. We have the coarse point pairs, we do the patch extraction, we do the fine point matching. And finally, if we have the fine point matching, we can perform the weighted procrusters. Here I need to mention that we heavily rely on the confidence scores that are coming from the structural encoder in order to calculate the pose estimate. Everything is differentiable, so we can train the network based on this. So here are the results. You can see the cups from the Lamar dataset. The original point cloud has 8 million points, and we are able to reduce this 8 million points to around 800 core super points and 86,000 fine super points. So practically, this is the cached map that is on the server. And you can see that the size of this map is 46 megabytes compared to the almost 5 gigabytes of the call map representation. So this is a huge compression that we could achieve. Here I also have to point out that in case of the fine points, you can see that the SNE coloring, we didn't have the semantic labels for the point cloud, but the network itself had to create this kind of semantically distinctive representation for the points in order to do the localization. So solely based on the Bose loss, we were able to create semantically meaningful classes for these points. We compared our results to different state-of-the-art benchmarks with single image-based methods and sequence-based methods, and we can say that our method is comparable or even better in case of longer trajectories, so the accuracy is quite good. And as the synthesis of the work, so we formulated localization as a point cloud registration problem. We improved the structural encoder for superpoint repositioning and confidence training. We designed the RF encoder and the fusion layer, and this is how we achieved good accuracy, small global map, and significantly higher speeds. We achieved 8 to 10 times reduction in the inference speed. So thank you for your attention, and please feel free to ask questions. And if you are interested in the detail, then in the paper we have much more details.
Thank you. Actually, we don't have any time for questions right now, and we need to go directly to the fourth one. It's longer than actually the 10 minutes. What about the fourth one? And the speaker, the talk is by Baram Baram Yahudi. Is it the speaker here? Baram Yahudi, Bruno is not here. Is online? Is the fourth paper order online? Okay, if no, we can. Okay. Should I find my microphone? You need to use Zoom.
Yeah.
The
but
Zoom. Okay, you
should
can directly present.
Should
Yeah.
I be active?
Yeah.
What's
You can
Oh.
use my, actually my,
Okay.
I'm open. You can use my iPhone.
Hello, everyone. My research is Gamma-Schmidt feature reduction for local feature descriptor compression. This is a joint research between University of Missouri and Washington University in Stanford. So for explaining my research, I need to review first the feature detection. So SEED is a handcrafted feature detector that has very interesting properties. For example, it finds the scale invariant key points using difference of Gaussian pyramid. And also it localizes key points by repeating 3D quadratic function to find subpixel extrema here. And also it computes gradient direction histogram to assign dominant orientation for rotation invariance. And also it creates a descriptor by dividing and normalizing the path into 4x4 grid. And also we can convert that to a feature vector of 128 dimension. So the question here is that can we decrease this feature descriptor without decreasing the accuracy? So there are some previous researchers. Some people use PCA, some people use Kenner PCA, but one interesting work was training deep learning. So I will explain that later. So there are several motivations for decreasing the feature set. For example, we have computational bottleneck in robotic application, and also we have memory and storage constraints. And also, if we decrease the feature of SIP, we can apply that for real-time application. And also, we can denoise the feature vector using feature reduction. So, the previous work that use deep learning model is a paper that the title is learning-based dimensional reduction for computing compact and effective local feature descriptor. The procedure is that they create patch and apply feature detectors like SIF, NKD, TFIT, and HardNet, and they create the descriptor of that feature detector, and then they train a deep learning model to reduce these descriptor features to lower dimensional descriptor. So they create 3 different deep learning models: self-supervised dimension reduction, unsupervised, and supervised. Because our method is unsupervised, so we are going to compare this method unsupervised. And so this is our procedure. We create patch, and also we apply SIF and HardNet, and then we create our feature descriptor. So in the next step, we use component-based feature reduction methods like PCA, Kenner PCA, and our novel method that is Gamma-Schmidt feature reduction. And also we create the low dimensional descriptor. So the limitation for deep learning model is that it needs training for each data set. And
The limitation for PCA is that it just considers linear relationship between the set or our vector vector. So the question is that is the descriptor of SIF linear or unlinear? So if it is unlinear, PCA doesn't work good. So this is our method, Gram-Schmidt feature reduction. So in simple words, we first compute the first two components, and then these two components are linear perpendicular, and then we want to create unlinear perpendicular component. So first, we compute the first two components, and then we project the first component on the second component. When we project that, we can find the common information with these two first components, right? So we remove the common information from the second component. The result is that the components are nonlinear independent. So we do that for the third component. For example, we compute the second component and third component and remove the information of second component from third component, and so on. So the result are all the features set is feature vectors are independently unlinear components. So to removing the common information, we need to use family function. If we use linear family function, the result is similar to PCA. Is converted to PCA. So the second order family function we use in this paper is, for example, the first and second component. And also we can use the third order also, and it is costly in computation. But if we don't have computation problem, we can use that. So what is the difference between our feature reduction method and PCA? So as I said, PCA works very good in the data set that information is completely linear, which the relationship is linear. But Gram-Schmidt feature reduction works good when the relationship between your data set and feature set are nonlinear. And also, we mathematically prove that Gram-Schmidt gives us more informative feature set. So, what is the difference between our method, Gram-Schmidt method, with the classical Gram-Schmidt? Is that in classical Gram-Schmidt, they applied on only vectors, but here we applied on family functions for the first time. So, after applying our feature reduction method on SIP and hardnet feature detector, we visually approve that our method works better than, for example, PCA. Here in the first row are the reference images. The first column is the query images, and the second column is the retrieve images. So the green line means the correct matches, and the red one means the error matches. So we applied on both kit toy data set and our custom data set in our lab. And for example, here we can see there are a lot of more correct matches in SIP GFR than SIP PCA. And also we compare with other feature reduction. For example, we compare with PCA and deep learning unsupervised method. And also we compare with Canon PCA asset. And also we apply this method on different data sets. For example, in like you see to an Aachen day and Aachen night dataset. And our experiment shows that applying Gram-Schmidt on 128 feature dataset gives similar result to original 128. In some cases, better results. And as you can see, our method works better than PCA unsupervised deep learning and kernel PCA in whole dimensional reduction. And also, we compare our method in different computer vision tasks, like patch verification, image matching, and patch retrieval. And also, we compare them in H-patch dataset that gives us easy, hard, and tough samples. As you can see in all feature dimensionality reduction, our methods surpass all other methods. And in some cases, for example, in 64 dimensionality reduction is surpass the original 128 dimensional C. And so for conclusion, as I explained, GFR works better than the other methods in different data sets like Aachen and InLAG and H-patch benchmarks. And we do not need any training data. And I think the most important key point is that every task we use PCA, we can replace that with kernel PCA to see if our results, if the results works better or not. Yeah, thank you.
Thank you very much. We do the time. We really have time for questions, and we move forward to the keynote talks. Okay, thank you. Yes, thank you. So I see Dr. Diaz is here. Can you hear me?
Yes, I can. Hello.
Yeah.
Good evening.
Okay. Yeah.
Yes.
Can you share?
Yes, I will.
Yeah.
Just a moment.
Yes. Well, screen. Let me introduce the first keynote speaker, and Dr. George Diaz. And Dr. George Diaz is currently a professor in Khalifa University in Abu Dhabi, and he leads the research and academic activities in autonomous robotics system. And also Dr. George Diaz is the deputy director for the Center of Autonomous Robotics Systems in Khalifa University. And he was actually the general chair for IROS 2024. And he has quite a lot of notable works. And in most recent, and that is in neuromorphic computing for AI and artificial perception, and which is also closely linked to his talk today. Yeah, Dr. Diaz, you can go ahead to present.
Thank you very much. Thank you, and good morning to everybody. Good night here in Abu Dhabi, and it is a pleasure to interact with you. This talk is more to motivating the people that is working and seeing so much importance in navigation, like we do in the robotics, and raise actually a problem that you are challenging with new things, with the computation of so much intense numbers that we have when we use CNS. So I will just briefly talk a little about the problem, the motivation, and then tell you where we are applying this neuromorphic computing for specific area that is the navigation aspect, namely in a way that includes the improvement of images for underground, underwater imaging, and also for visual inertial aspects for pose estimation. In fact, navigation for us, as we know in robotics, is very important. All the time, we are doing this kind of combination of vision for using, let's say, a mechanism to do navigation. This is the aspect that this workshop also address along the time, as we mentioned in the beginning. And actually, the idea that we have nowadays is that the use of vision mainly are supported decisions for the navigation using this kind of virtuous cycle that is you do an observation of the world, you reasoning about what you see, and then you impose some kind of motion on your vehicle, and you do sequentially and in a cycle all this process. And this process that you write it by these 3 states that is written here, in fact, the application that we have nowadays in hardware is software that's running under platforms on the hardware that typically use modules of softwares that use as the stacks. You have stacks for perception or sensing, the stacks that are related with the decision support, and of course this kind of way of operating have been really giving good results along the time for us. But we need to see that nowadays many of the algorithms that you run on these stacks, use machine learning techniques. And what is happening is, because of the models that you have on the machine learning aspects, the quantity of the energy that you spend is enormous. So, you can see, for example, situations like this, where in these graphics along the years, the deep learning techniques increase the quantity of flops, megaflops that you need to do on your computing for doing your algorithms. And this is automatically, increase the quantity of energy that you spend. And if you look for the different graphics that you see here, you see the increase of computation aspect that is related with the energy itself. So partially the problem comes for the energy, but also the quantity of the memory that you need to use. And many of the things that you have, in fact, are due to the fact that we are using not obsolete, but a kind of architecture for computing that are not really the good ones. So you see the AI algorithms running and scaling more and more complex, and you see the energy growing. And what happens is the quantity of details on the way we are doing the computing are really extremely evident. For example, you see the traffic between the memory and the CPUs or GPUs a little increase it. You need a little more better transmission on the buses that we are using. You increase the temperature of your microelectronics. There are problems sometimes with the interaction of different modules that you are using. The latency increase. The battery by itself become less operational on the time, and actually push us to looking for alternatives. And the alternatives that we have been doing now, and looks like very interesting, is trying to do a bio-inspired mechanism, is like using another kind of computing that is based on spikes. In fact, this kind of way of doing computing that is very close to the way we as human beings work, by spiking, is very interesting aspect, but definitely not so much developed like the classical way of doing computing, using the CPUs, more recently the GPUs, using electronics that maybe they are very efficient, but very close to barriers that you have on the physical systems, on the energy they consume, and this is push us to see the situation of computing very seriously. Because if you continue this way, you know, developing algorithms that, you know, increase the quantity of need of transfer of memories, or the energy that you use, or the operations that you use, probably we increase very much the energy, and you have a system that, you know, become a new consuming of energy that was not expected. So the performance we link it with is consuming, and usually looking for alternatives. And then now alternatives exists, and then our alternatives exist. Some cases in previous workshops that we have, we see the use what we call it neuromorphic but sensing with event cameras, that they, you know, they look more the event itself. They just register when you have some differences in the image, and this is very well explored in the robotics side. But it's not just that. We can have also another way of doing better, you know, processing by exploring better the memory that we have, and maybe looking not for the operations, but for operations that are registered on the memory. And instead of doing the computation, you just use access to lookup tables that already have the access of the result that you like to achieve by the operation itself. So instead of you doing the operation and using electronics to do the operation, you just fetch the result from tables with results, you know, in memory. So this in-memory computing mechanism is very interesting. Is another kind of architecture that is currently explored as alternative. We are not doing that in our case. We're exploring a little more the idea of neuromorphic computing, that is somehow the idea of spiking, using the spikes that are, you know, the mechanism of organizing the information such way that you can achieve the similar performance as the you compute with normal CPUs and GPUs. And there are really interesting effects on using these mechanisms, also using the machine learning tools. And this is effects that I will talk a little more about it. So this is one of the cases. It's just one of the cases that I just showed to you. Here they explore different kind of architectures using GPU, using LOI, that is another kind of spiking CPU, let's say, or Jetson. Some people know this hybrid or mechanisms. They use GPUs very close to the CPU itself, and you see different kind of energy involvement on this kind of different kind of algorithms that we can show along the years that the people is exploring. This is just one reference that I give it to you to tell that in fact, the GPUs are very interesting, but the consuming they use is sometimes very abusive, and there are people looking for mechanisms for pruning their algorithms, trying to reduce this kind of mechanism of doing the computing a little more efficient, but always staying with the mechanisms of the operation that includes always typically the multiplication and additions. And this is not what spiking is using. Actually, the spiking is using a little more easy way, as I will show to you. One interesting aspect that we use, we are trying to do it also in our area, is that the effect of the energy is really important. And this is for us is extremely important, because is the fact that in our applications on the ocean, we have situations that are very relevant to increase, for example, the visibility of the lights that you have, you know, the quantity of the energy that you have on the devices that are under the water. You don't have, you cannot rely on GPUs or clouds of computing that you have available when you are in the place where we have capacity to link with internet or something like that. So when you have devices that are exploring places like these ones, we need to be very, very rational on the way you spend energy and the way you also do the performance to make these algorithms running. And this is putting us in a very strong challenge to improve the way we do it. And the idea of doing the underwater navigation is really a very hard environment where we can, in fact, develop new algorithms that improve the algorithm itself, let's say the throughput that you can have on the performance of the algorithm, but you can also improve the way the hardware is efficient. And in our case, our contribution very recently is more in two areas: the odometry estimation itself, the pose estimation and the visibility aspects. But we can improve also on other modules, of course, but we mainly concentrated in these two aspects in the work that I'm presenting today. So our system, basically, we are trying to teleoperate underwater devices. We're trying to do it with optic devices. This is more or less the architecture that we have. We have the user that are operating a device far away. We have the optical controller that we try to use the optic way to avoid collision avoidance when you are operating a device. And you are concentrated now in the visual module, the image processing, and also the neuromorphic mechanism for compute the pose. That is very important for retrieving to the operator the position and the orientation of the device under the water. This is mainly our mechanism. So when we do this spiking neural networks, the mechanisms to really do it, actually the conventional way is very well known. This linking, a neuron, we call it lift neuron, where you spike according to some kind of leakage and conservation of energy, and then spike when the condensator are just charged. And this is a very single mechanism that we can use, like combining the information that you retrieve by spikes that you generate by, for example, event cameras or any kind of device that you generate the spikes, and you can compute on or hardwire the spikes such way that you integrate or you fuse the information between different sources by the way you sum them or by the way you multiply them. So the spikes are in fact a mechanism that you can play by doing the spikes in different forms of modulating. You can modulate the spikes by the amplitude when you fire, or you can do it by the frequencies that you do the number of frequency of spikes that you have to increase or give a number of let's say representation of the information that you got. So basically the spike mechanism is quite interesting and give a very good way of, for example, as we can show very briefly here, to do the multiplication or doing the sum that is combining the information. So this kind of thing is really not using so much the mechanism as we have for additions and multiplications when we use the common digital mechanism. This is a new way of computing, of course, and along the time, and this is just reference that I will give it in the end. You know, there many of them, you know, operate the previous, you know, first steps that we have done on this kind of using of spiking. We don't have so much, you know, much resolution on the data that you use. We have some lack of generalization of areas where we can use the things, and in fact they give space and some kind of gap for looking for better ways of computing using the spikes as a mechanism to you know, do computation specifically or using this mechanism. We are not unique persons to do that. Let me tell you that particular aspect. Some kind of communities are exploring that. In our case, we initially start by using what we call it typical, you know, spike neural networks without any kind of much more than just transforming the numbers in a static way to spikes. It was our first approach for image enhancement mechanism, but later on we start exploring a little more efficient ways and more real-time application with model ways of using transformers, using adaptive ways of the transformers, and then hybrid way of combining different kind of modules for different sources with different rates of operating. The inertial, for example, with images that have different rate of giving signals, and this is really a very interesting aspect. We don't need to looking for the clocks that we normally are forced to use when we use classical and algorithms for doing you know, a computation of visual inertial. So in this case, in our case, we just explore that way. We're using this kind of idea for spikes because, in fact, we don't need to go on the classical digital systems. So this is just let's say results of our exploration of this spike and neural networks that we do it using you know, with a very specific way that we do the convolutions mechanism. In fact, you can imagine that we can you have your convolution mechanism, but the convolution mechanisms become like fire. The convolution, but depending of the values that you have for the firing. So we don't use any more numbers, but you use just thresholds when you spike or not spike. This is just a general mechanism that we can emulate somehow the mechanisms that you use in CNNs as we can do it also with SNNs. So basically, the mechanism is quite simple. And what we start to learn is that this kind of mechanism of firing, the first attempt is to make these thresholds for firing to be, you know, defined specifically in certain threshold, but we develop a technique for dynamically have the threshold by learning the learning aspect on the threshold itself. So the learning on for us, the learning aspect is the learning when you do the firing. So the firing is related with this kind of formulation where when you do you know, this kind of computation, when you use the mechanism of pass for the backward, you adapt the threshold itself by the learning mechanism that you use in the neural networks. But in fact, instead of using you know, typical thresholds, that when you use the comparisons, we're just using the fire mechanism as a mechanism to fixing the learning aspect. So let's put it in such way that the firing is related to the learning itself, and this is give a mechanism to improve a lot the energy, as I will show to you later on. So basically, this is the typical mechanism that you use for the inertial, and you know, the mechanism is simple. You threshold the things in a certain way where you give the numbers and the fire become the spike representation that we see here typically. So basically, this is the mechanism that you use when we try to integrate this a little more on the transformer mechanism. We start to have on the transformer a mechanism of self-adapting, also this threshold, and this is really something new and novel from our side, that we really use it as, we call it adaptive spike-based self-attention. Aleph, that is our mechanism of computing this adaptive neuron that is aggregated in this form that allow us to have a mechanism for self-spiking mechanism that is different from the conventional part. It is that is linear way and how we do it in the conventional approaches. So our mechanisms allow us to really improve a lot the energy that we have. Algorithmically, we can make it, with performance that are very close to the normal performance that we have in GPUs, and you can still have a lot of saving of the energy, including certain situations also when we have algorithms that are really improving also the energy itself by using GPUs. This is the qualitative approach that I've just showed to you. Maybe you can see here the first row is the typical mechanisms that we have on the images and the input that we have. This is the reference that we have for our comparison here, and this is our transformer mechanism that in some cases, as you can see, some details can be better, defined, as you can see in this part. This is maybe controversial from the perspective of qualitative analysis. We did really this quantitative analysis a little more deeply on our side, comparing the accuracy, the similarity index measures that are really important for imaging analysis. We also did common algorithmic performance metrics, and we joined to this kind of mechanism of improving our algorithms and other oriented hardware metrics that are related with, the metrics are important for the hardware side, like latency, throughput, number of operations that you need, and of course, hardware cost and on-chip memory. When we start doing these kind of studies, it was very interesting that the state-of-art methods, many of them trying to improve the energy. I've just put you along one that was a reference here. The energy ratio here is quite high. The energy is really low here. The performance is quite not too bad, but the number of operations, is quite, very low. And the remaining comparison we have is quite good for the state-of-art. But when you compare with our method, we really did a very good performance compared with this one, and also to the other methods. Our method, actually, when you use the spiking adaptive, we really achieve very good performance compared with another ones. The numbers are very close for the algorithmic part, but when it comes to the energy, we save a lot of energy by using this kind of approach for computing the algorithms. This is one overall performance that I just showed to you. In the beginning, we just using some kind of data sets here, and you can see how this we change the energy consumption also by the image resolution that you have for this second table here. You just more than double the resolution of the energy, but the resolution of the image, but the energy still more or less controlled in a certain way in terms of joules. And of course, the quantity of the operations are quite high, of course, but still the energy quite low on our case. So we did studies about using different ways of doing the threshold, fixed way, adaptive way, or both adaptive and different kind of organization, how you combine the information itself. And actually, the best way is combining the information together with the adaptive, as you can see here. And all these kind of results trigger us for different kind of evaluations, like I'm showing this to you. Sometimes you see some flicking here that from the way you are transmitting the image to outside. But the aging are quite good when you compare and use it every day on the devices in our wave tank that you have on Caliph University. This is just one example of our results that we have. This is another comparison that we have. Maybe here deserves a little more time to see the results. This side here is the use of this spiking transformer adaptive way applied to images on different kind of images in different kind of conditions. This is conditions obtained outside, and the first one is conditions that we simulate under our pool, and these ones are from conditions that we capture from data sets that we have from another groups that we are using for our experiments. And the energy that we use again is quite useful and is quite let's say suitable for the kind of devices that you are putting under the water. Another aspect that we explore is also the way you compute the motion itself. This is just the first step that we have done for the ergo motion estimation that we use later on for computing the visual inertial aspects. So here, the first studies that we have done is using, cameras are looking for, scenes under the water where you see fishes going around, and we can separate our ego motion from the typical static aspects that we have, and also the moving aspects that we see. And actually, it's very interesting that in our mechanism, we retrieve quite very good results from the separation of this ego motion in the time, and we use this kind of mechanisms later on to improve our real-time application on the data sets and also underwater navigation that we use in our system. So we develop this kind of post-estimation, using the image itself, where we use typical, mechanism of computing the images, like, adaptive spiking, like I showed to you before, and the inertial mechanism that is different, totally different ways of computing information that typically is, rotation, accelerations, but you transform this IMU data later on spikes, and the mechanism is coming from the normal physical aspects to the spikes that you aggregate them here on the variable that you refer here as SFI. Here, the reference is more the flow that you have in the images, and the combination is done later on in a layer that we just use the spikes together with the mechanism of automatic thresholding to dynamically combine and fire the system in a certain way where you can generate the final result of the pose itself based on the fixtures and the motion that you got it from the images and together fuse it with automatically the inertial mechanism. So there are no other things like use the numbers of numbers means spikes here that you got from the image and from the inertial system itself to feed the architecture that you have mechanism to self-adapt the thresholds for the spikes for later on generate and reiterate again, the spikes to be, values that you can use as translation and orientation itself. So basically, the mechanism that we have in this eye and hybrid way of using the post-estimation, where the images are transformed to the spikes and the inertial data is transformed to the spikes. We don't really care about any kind of clock, and the information is, related together, and learning the thresholds in such way that we can later on retrieve by back propagate again the number of the spikes that we have to numbers that we associate to orientation and translation itself. Velocities and translations are really the things that we have in the end. This is what we have in the end. Delta translations and delta orientations that you have, like equivalent what you have nowadays for any kind of visual inertial mechanism. But the first stage that we have done, we use also as in the image data, we started by using conventional adaptive neural networks. We do the first mechanism that way. Then we just change this mechanism to use the spiking mechanism. And what was interesting is that when we apply the self-adaptation mechanism, we really improve very much the results, as you maybe can see it here in the results here. The results are results for sequence that we have, and we have the mechanism of sometimes it's difficult to see the reference case with they superimpose. There are some situations where the reference appears, a little more evident from their side because the color is more evident, but the superimposing show that just very few cases you have, some errors on compared with the baseline. So this is just to tell that, the mechanism when you compare the state of art with this spiking mechanism, this using the state of art and the spiking mechanism, the performance is almost the same in terms of algorithms, but evident fact is that the energy consumption is totally different as we know from the previous cases that I showed to you. This is just another way of seeing the results, not in the X, Y, and Z, and that this is the results, along one of the sequences, one dimension. And this is for another one. And you see in some situations you have certain discrepancies, but it's not too much evident when you have the aggregation along the time. So it's quite good to have some kind of mechanism to do it. And we made some comparison actually for different kind of methods using CNNs, when you do it outside without, not really under the water, and you just using typical mechanisms of comparing them with our CNNs. And what happens is that when you use our neural mechanism is a fact that you know the sequence give very interesting results when and very comparable to the other sequences. Actually, one interesting aspect that appears that you really improve a lot the effect of the energy. Actually, this you know, speed up that I showed to you here, comparing the energy baseline with our mechanism neuro VIO, you arrived to a speed up of improving like 80% of the energy you save with the neuro VIO. You know, when you you know, in this case, the fixed threshold and the adaptive threshold in this kind of operations is not too much evident, is very comparable, but compared with the baseline, no spiking mechanism is really totally different. And you know, it's just when you compare with that, with the baseline, is really you know, totally quite performance mechanism. So this is some of the reference that I like to tell you. I think it is important to raise the situation where we need really to think about how we use this spiking mechanisms of doing computing. In the lab, we have all this team working somehow on this area. And if you are interested to look a little more about this computation mechanism, please feel free to address this kind of parts of the publication that we have done. And of course, please come to the community of trying to improve a little more the way you do the computing and save, you know, some energy for using this kind of very good algorithms, but not using so much energy by using a different kind of paradigm of computing. So thank you very much. This is what I like to just address here, and I think I'm keeping it on the time. You know, I think I have 40 minutes to finish, and I still have 1 minute for any kind of question that you may have. So I think you are muted now. I cannot hear anyone.
Okay.
So,
maybe one question for one time for one question.
Yes.
Any question? Actually, then I have a question. And actually, during your neuromorphic computing, and you put quite a lot of emphasis in the scenarios that lighting condition is not very well. And for those scenarios, that is quite common and quite actually regular lighting condition. Do you think the same system will work as the same as what you have introduced in your presentation?
Yes, you know, it looks like when you see qualitatively is okay, but what is important for us is the energy that you spend. So I think when we talk about new algorithms here, when you are trying to apply these technologies like spiking, you should start increasing the way you compare algorithms. And this is when comes, I'm sorry, I'm repeating, you need to use the algorithmic performance metrics anyway, plus these ones. Because when we use new way of computing, all these kind of hardware metrics will come. So by the way you are computing, we need really, you know, pay attention to the fact that, you know, there are another effects that could happen. Maybe we degrade sometimes the performance on output, but you gain a lot on the energy side or in the quantity of numbers that you need to apply, or memory, you know. So I think it's very important to mention the fact that we are not using just algorithmic performance metrics, but we extend this to another kind of metrics that are more hardware-oriented metrics.
Okay. Thank you very much. Now let's welcome
you.
the second. Yeah.
Thank you again.
Thank you very much, Dr. Diaz. And let me introduce the second speaker, and Dr. Lorenzo Corenzani, and who is a professor right now in Northeastern University, and also the President Joseph and Aaron Chair in the College of Computer Science. And before joining Northeastern, he was actually a research director in Meta. And before that, he was a professor in Dartmouth College. And his work has been recognized by many different agencies, such as NSF Career Award and Google Faculty Research Award, 3 Facebook Faculty Awards, and the Fulbright Scholar. And now welcome Dr. Torres-Sani. Is my pronunciation correct?
Good. That's good.
Okay.
Do I need to plug in my laptop or is it
I think
like
good.
this?
I think
Okay.
good.
Do I need to unmute myself here?
You can find, yeah. And I think you have. Oh,
Probably not.
probably not. Yeah.
Okay. As long as people online can hear.
Yeah.
me. Okay, good. All right. Thank you so much for the introduction and for the invitation to speak at this workshop. So the premise of my talk lies in the title. I believe that our research community has made dramatic progress on teaching machines to see, but many problems we care about actually require more than perceiving the present. So consider, for example, the following application scenarios. An AI agent on smart glasses that warns you about a potential pitfall of an action that you are
Lou, I'm sorry to put up. I don't hear anything. This is some problem from your side?
Can you hear me now?
Yeah. Now it's something, Lawrence. Yeah.
Can you hear us now?
I hear myself, I hear well now.
Can online people tell us if you can hear us?
I can hear myself. There's this speaking. Yeah.
They cannot hear us. I am
No,
muted.
I can hear. I can hear you.
Oh, you already unmuted.
I am unmuted.
Let's switch. Can you hear us? Can online people hear us?
Yeah, I can hear very well. You also. Hey, you.
Okay.
Yes.
Okay. Yeah.
Okay.
But the online people, they speak, we cannot hear.
Oh, then when they speak, you cannot hear.
I can hear from them.
Okay.
Okay.
But they can hear us now.
They can hear you.
Okay, good. All right. Okay, then I'll proceed. Okay, as I was saying, so anticipation, I believe, is one of the key ingredients for AI assistance because, well, an AI agent must obviously know at any time not only what the user is doing in the present, but also what is going to do in the near future in order to provide relevant contextual support. But consider the following three moments. Each of them admits many possible futures. And if you simply train a model to minimize the prediction error, the risk is that the model will try to hedge or average across all these possible futures and would end up getting it wrong every single time. So to better understand the problem, let's look at how the task is typically approached in the literature. So we assume we are going to give as input a short egocentric video clip taken from the wearable camera. That's the start clip. Optionally, we may also have available a goal clip in the task of planning, which, as I will discuss, closely relates to the task of anticipation. So this video context is then passed to a causal predictor, such as a transformer, which generates a sequence of intermediate representations, Z1 through ZH. And since we are interested here in semantic prediction rather than pixel level reconstruction, it makes sense to use fairly high level representations, such as latents from the VJEPA encoder. Then these latents are passed to a readout module, which is often an MLP, which maps these latents into discrete action levels. So this is a very general pipeline that has been used heavily in the literature, and it can be easily instantiated actually to address simultaneously three different tasks. Action anticipation, which is what I discussed, where you do not have the goal given as input. Procedural planning, where instead the goal is observed and given as a goal clip. And finally, event prediction, where instead you want to perform multi-way classification about a future outcome. And while this pipeline is fairly standard,
a lot of work has investigated two fundamental questions. The first is there a conditioning signal that can help us in disambiguating the future? Because pixels alone, as we will see, are often not sufficient. The second question is, well, what's the best latent space to perform the prediction? And you'll see that this actually heavily affects the performance. Okay, so let me get to the first question, which is about the conditioning signal. And so a natural choice is to use language as an additional auxiliary input for the causal predictor. For example, we can describe in words the intent of the camera wearer, such as whisking the eggs. And in fact, obviously, this narrows down quite a bit the set of plausible future actions and has been heavily used by prior work. However, language is coarse. There are many different ways of whisking eggs. There's a gentle way that incorporates the eggs smoothly, and there is an aggressive one that would cause splattering the eggs outside the bowl. And it's clear that the difference between these two ways of whisking eggs is not captured by the description of the intent. It's captured by the actual motion performed by the user. Interestingly, recent work that is actually going to be presented here at CVPR has shown that for the case of offline recognition of past actions, the camera trajectory, like the visual odometry information estimated directly from the wearable camera, is a very revealing signal for discriminating at a fairly fine-grained level actions. So the work of Xu et al. Has shown that often just taking the camera trajectory as a signal can enable fairly accurate action recognition. However, in the context of action anticipation, the trajectory of the camera that we are interested in is the future camera trajectory, not the present or the past camera trajectory. Yet it's interesting to ask ourselves, well, if we had access to the future camera trajectory, would it help our anticipation task? And so to answer this question, we carried out a simple experiment on a toy problem of analyzing a user shooting a basket. And we wanted to train a predictor on the outcome of the shooting from just the pre-shot context. So a short clip captured from the wearable camera of the person that is about to shoot the ball. And so if you use pixels only, you get a 56% accuracy, which is just above near chance. Now, if you use the future camera trajectory as an oracle, you actually obtain 93% accuracy. This is not surprising after all. What is surprising, however, is that the future camera trajectory itself is partly predictable from the pre-shot clip, from the given context. And if you actually force the model, the predictor, to condition on this candidate future trajectory, you can achieve an accuracy of 81%, recovering almost all the gain of the oracle without actually having seen the future camera trajectory. Now, this is a toy problem, but we actually confirmed a similar pattern on the full EGO-EXO4D atomic action benchmark, which contains over 8,000 action in an open vocabulary. And what you see here is a plot that shows the improvements in predicting future latents over pixels only. So when we use the oracle future trajectory, we can cut down the error 20 times more than when we give the oracle action labels of the future actions. Okay, and so this essentially demonstrates that motion information is actually more salient than language description of the actions. Okay, and so these two diagnostics essentially inspired the design of this system, Trudge Pilot, which you see here. So here's the idea. We take the video context from the wearable camera, and we use it to retrieve K candidate future camera trajectories from a bank of trajectories. Then we take each of these K trajectories one at a time, and we roll it through a causal predictor as a conditioning signal. And this is a very important operation because it basically forces the causal predictor to commit on one particular future. And this allows the model to avoid essentially averaging overall possible futures. So each trajectory essentially generates a candidate action plan, which we then rank using a trained scorer in order to find the plan that is actually more plausible. Okay, let me come to the second question that I brought up at the beginning. What latent space should we be using? So a natural choice is to roll out sequences of latents in the raw VJPA space, which is quite popular, and simply take the sequence that lands closer to the intended goal. However, this works only if distances in the VJPA space match action similarities. And we found this not to be the case, as shown in this plot, where we show that the blue bar, the average, which measures the average pairwise distance between VJPA latents representing different actions, is actually higher than the pairwise distance between latents representing different actions, but belonging to the same video. And this happens essentially because VJPA optimizes visual continuity rather than action similarity. And so to address this problem, what we propose instead is to avoid decoding directly from the VJPA space. And instead, we project to a language-shaped action space. We learn this action space essentially by contrastive learning using EGO-VLP embeddings, which are an extension of the clip representation in the context of egocentric perception. And so this essentially forces the latents to have distances that match action similarity. And an additional benefit is that the readout of test time then reduces to simply an nearest neighbor operation on the EGO-VLP action bank. And so this means that you no longer need to train a separate classification head for different downstream tasks or different taxonomies. Okay, let me show you some of the results that we have obtained on a variety of benchmarks. Here, the evaluation is on EGO-X04D atomic actions. On the left, you see anticipation. On the right, you see procedural planning, where the goal is also given as input. And both plots show performance as a function of horizon. So essentially, the number of actions that we predict into the future. And the performance of our system is shown with the solid red line. And you can see that it dramatically outperforms the green line, which is a strong video language model fine-tuned on this particular task. It's also interesting to notice that the red line does a lot better than the blue line. The blue line is our same system, but without conditioning on the candidate future trajectory. And finally, it's interesting to notice the super strong performance of the red dotted line. That's essentially the Oracle model, which uses the true future camera trajectory. And so this really shows the saliency of the signal, and it also explains why our system does well on this task, since it tries to predict essentially the future visual odometry. You see a similar pattern on procedural planning. We have also compared our system to much stronger structural planners, such as Viterbi PlanNet and PDPP. These are state-of-the-art procedural planners, and yet our model that leverages this idea of anticipatory visual odometry outperforms all of them consistently, especially over large horizons, over large predictions into the future. Now, I want to stress that actually the entire approach does not require specialized hardware. In fact, we tried training on camera trajectory estimated via visual odometry from RGB videos, and we found that our approach actually works as well as when using the camera trajectories estimated using instrumented camera rigs like ARIA. Okay, let me transition to the second project that I want to discuss today. And so this is going to be about procedural guidance. So imagine, for example, a user wearing smart glasses and trying to replace an alternator for the very first time. So what we want here is an AI system that essentially understands the scene, localizes the parts and the objects, and provides step-by-step guidance in fluid language to the user on essentially guiding the user on how to execute the task. And specifically, we want a system that can really identify the special configurations of the objects on the particular bench of this user and should refer to these elements in the guidance. Here is a formalization of the problem. We are given video history as input, typically taken from a wearable camera. This essentially captures what the user has accomplished up to this point. We also give a natural language description of the goal of the task. And then we want the model to generate this fluid description in language of what to do next. And since the description is in free-form language, we use a LLM as a judge to evaluate the accuracy of the guidance with respect to the ground truth. And we use 7 established benchmarks to carry out the performance evaluation. We consider 2 different configurations of this model. One that we call Socratic, where we essentially take a frozen VLM to summarize the visual history into a sequence of steps that are observed in the given video. And then the entire planning then happens in language space. And we also have a variant where instead we feed directly video tokens to the planner, which is then a fully multimodal planner. And the fundamental question here is, what kind of supervision should we be using? And if you look at the literature, there are essentially 2 data sources that have been used. On one hand, we have small, manually annotated data sets such as Crosstas, Coin, where human annotators have painstakingly labeled individual frames in videos with step information. And the quality is great, but typically we have only annotations for a few tasks and only few video examples per task. On the other hand, we have web corpora, such as How to Hunt a Million, which includes over 1 million instructional videos, but no annotations whatsoever, except for the transcribed narration from speech provided by the demonstrator. And so the typical strategy in the past has been, let's train a model first on the clean data, then deploy the model to pseudo-label the web corpus, and then use the high confidence pseudo-labels to retrain the model. But as I will show you, this actually leads to degradation in performance because of pseudo-labeling error. So the observation in our approach instead is that, well, trying to extract clean labels from these noisy web videos is really hard. But conversely, what is much easier is to take a proposed candidate plan during training and check it against the web corpus. I'm saying that this is much easier because we can actually do it in language space, because the plan proposed by the system is just a language description, which you can compare directly to the narrations of the instructional videos. And so this means that we can bypass altogether the problem of processing the videos, the raw videos, segmenting them into steps, recognizing the steps, and so on. And so here is how it works. During training, we essentially ask the model to roll out multiple candidate proposals. And then we take each of these candidate plans and match it against all of the narrations in the large web corpus. And we use the alignment scores as reward signals in a reinforcement learning optimization using GRPO. Now, in order to achieve scalability to this large size data set, which includes over 25 million narrations, we exploit pre-computed sentence embedding for the narrations, and we adopt a 2-stage procedure for alignment. In stage 1, we apply a fast retrieval method that finds the top 25 narrations given the proposed plan using a fast, greedy, monotonic alignment. And in stage 2, we re-rank these 25 narrations according to a more refined and more accurate global alignment method. Now, an interesting subtlety here in the reward computation. So in order to compute the alignment scores, we actually use the complete proposed plan, which includes the history as well as the completion proposed by the method. It's fundamental to use the history because that essentially serves as an anchor to find the relevant narrations in the large corpus. But the downside of using the history is that it also contributes to the alignment score. Whereas what we really want to measure is the contribution provided by the completion without the history. And so to really compute this, we actually score twice. We score the complete plan, including history and proposed completion, but then we subtract from this alignment score the alignment score of the history alone. And so this allows us to really measure the alignment improvement, the continuation adds beyond the history. And here you see side by side the results of using the same exact corpus, how to 100 million, in these two different fashions. So the red bars represent the result of pseudo-labeling for three different model sizes, 0.5 billion, 3 billion, and 7 billion. And you can see that in 2 out of these 3 cases, the red bar is actually lower than the gray bar, which represents the base model before the pseudo-labeling, before the fine-tuning. So this means that essentially the pseudo-labeling often actually leads to degradation. Whereas the blue bar represents the performance achieved by our system, which dramatically improves the performance of the base model. We found that our reinforcement learning optimization improves not only the accuracy, but also produces plans that are procedurally more diverse. And this is shown in this plot where the x-axis measures the diversity of different rollouts for the same given video history. And so you can see that compared to the base model, our method achieves higher accuracy and higher diversity. Conversely, SFT actually leads to a degradation along both aspects. And specifically, it leads to a lower procedural diversity because it forces the model to reproduce the single ground truth plan for each video example. Whereas our model actually rewards diverse plans that are supported by the entire corpus. Okay, let me move now to the third project I want to present today. This essentially is going to move us from single user activity to coordinated activities. And this is, in my view, a very important topic because if you think about it, most consequential settings actually do involve observing and supporting team efforts. And in such scenarios, it is not sufficient often to simply localize who does what, when and where in the video, but the model must also reason about the intent of the individual subject or the effects of potential actions, or may even need to simulate what-if scenarios in order to support the coordinated plan. And so when we started looking at these problems, we looked for good data sets, and we identified a very significant benchmarking gap. And this benchmarking gap is due not only to the fact that most video datasets actually do not contain coordinated activities, but it's also because, well, most real-world video datasets actually do not have any annotation supporting causal or counterfactual reasoning. They only test perception or temporal reasoning. And this happens because it's actually really hard to collect causal or counterfactual reasoning annotations on real-world videos representing daily life. So to address this gap, the community has developed synthetic environments such as Cleverer or Fire, where simulations can be fully rendered, but the downside is obviously that these environments are synthetic and they lack the realism of actual video and human-human interactions. And so we propose to address this gap by releasing a new large-scale benchmark that we actually announced just a couple of days ago. It's called SVI Bench. SVI stands for Strategic Video Intelligence, and it's built on top of 35,000 hours of team sports broadcast videos. We have hockey, we have soccer, and we also have basketball. And the benchmark essentially tests 4 different capability levels. We have perception, where we test the ability to determine who does what, where, and when. We have reasoning, where we test the ability to predict objectives, but also effects caused by actions being taken. We have simulation, where we test the ability to generate what-if scenarios. And finally, we also test agency, where the model must autonomously make sense of millions of video clips to extract evidence in order to answer a very challenging question. And so the natural question is, why did you pick team sports? Well, they actually check several boxes that are relevant for us. First of all, team sports contain lots of interesting examples of human-to-human interactions, coordination, also adversarial behavior. But most importantly, they contain, for free, verifiable outcomes of cause and effect in terms of objective measures, such as shooting or scoring outcome, possession maintained or lost, and all of these signals. They also come with very rich metadata that allowed us to really scale this data set to unprecedented size. And on the left, you see how our system compares to relevant prior benchmarks along the most meaningful dimensions, such as number of video hours, number of annotated actions, number of expert commentary sentences, and so on. And pretty much along each of these dimensions, our model outperforms prior benchmarks by more than 1 order of magnitude. But the most important aspect of our benchmark is that we believe it's the first multi-agent real-world video dataset supporting training and testing of all 4 capabilities. So in order to build this benchmark, we leverage all the modalities available. So we obviously have lots of raw video, but it also comes with expert commentary provided by the broadcasters. But most importantly, we have also play-by-play logs. These are essentially annotations provided by professional annotators employed by the sport leagues and describe every few seconds what happens in great detail in the video. We also have game reports written by journalists, as well as game and season statistics. And so we built a data engine that processes all of these modalities together in order to generate automatically benchmark task instances. And so this data engine takes care of temporally aligning all of these modalities, resolving multiple identities to the same person or the same team, and then generates automatically benchmark task instances using LLMs. We also have a quality control stage that removes a hallucination by cross-matching the task instance against the original modality. And we also make sure that each instance is difficult to solve and requires visual understanding. So let me show you some examples of these benchmark task instances. And I'll skip altogether the perception capability level because we are accustomed to seeing those kind of tests. And so I'll focus on the higher level capabilities that do build on perception, spatial localization, and tracking. So for example, in this case, this is an instance of strategic causal reasoning where we give the model a full basketball game to watch. And then we ask the model to identify the strategic defensive change made by one team at the beginning of the 4th quarter. And if you look at the answers provided by AI frontier systems such as GPT or Gemini, they look very plausible, but they're actually very wrong. So it really shows that these models are not capable of actually connecting the perception to the causal reasoning. Here's another example where we ask the model to perform outcome forecasting. So we asked the model to predict which of the two teams is going to win the game at 4 different times in the game. And the first 3 times, the model actually picks the wrong team with a self-declared confidence of 99%. And then the 4th time, it flips completely its decision, still with a declared confidence of 99%. And so this tells you really that the systems have no understanding of the ambiguity of the event they are asked to predict. And also they have no sense of their own uncertainty. Here we have an example of future video generation. So in this case, we give the model an initial frame and a language description of the actions that we want to see played out in the future video. On the left, you see the ground truth video. On the right, you see the generated video by the best model. And you can see that the system is barely able to synthesize players at roughly the right location, let alone render the actual desired action. And so here you see at a snapshot how performance degrades across the capability stack. The best model performs at about 70% on perception tasks, but then performance falls down in the 40s and 50s for causal reasoning and counterfactual simulation. And then the model collapses to only 5% on the agency task. So why does this happen? Well, one possible explanation is that there is error compound because each of these capability levels is relying on the previous capabilities in order to address the task. And so we try to answer this question or this conjecture by performing an oracle experiment where we essentially replaced the video input with a ground truth textual description of everything that happens in the video. And we found that actually on many of the tasks, it makes no difference. It provides very marginal gain. The only task where this leads to significant improvement is agentic reasoning, where GPT goes from a 4% performance when applied to video to a 54% performance when applied to ground truth textual evidence. So this is a dramatic improvement that shows indeed the importance of perception, spatial localization, tracking. But at the same time, it also tells us that there is 46% of questions that GPT cannot answer even when provided perfect perception. So are the tasks simply too hard to solve? Well, not quite, because actually expert humans can solve them. And it's quite interesting to actually look at the gap between human and AI performance across the different tasks. And in a sense, it mirrors the capability cliff that I showed you earlier. For example, we found that on perception, AI is almost on par already with humans. But then when we move to the higher level capabilities, we see this gap widening considerably. Okay, so I hope I convince you that across these 3 different projects, we really identify models, capability, and we see that video models have indeed learned to see, but there is a lot more work to do on teaching them to anticipate, guide, plan, and perform complex reasoning over these videos. So I want to acknowledge the contributions of all my collaborators in these three projects, and I'm happy to answer questions if there is time.
Yeah. Any questions?
Let's talk, Lorenzo. For the last part, I was wondering, are you using any extra information? So when you do sports game, you have some rules. Are you using this kind of information to, because theoretically, you can use this one to encode and place your interaction to get better results?
Yeah, excellent question. We do not explicitly encode knowledge about the rules of the game. I mean, we are leveraging pre-trained VLMs, which I assume have some form of embedded knowledge. However, we have lots of results actually that show on fine-tuning these models. And we consistently see dramatic improvements in performance, when fine-tuning, which means that, yeah, they can pick up, even more information by actually watching the games, which is precisely one of our objectives.
I have a question on the action prediction model.
currently solid text-based that you're trying to do. You're predicting the actions in language. There's a lot of models that are coming out that are doing actions in joint-based actions for the robotics. How do you think the research will combine with robotics and what you are trying to do on action predictions?
Yeah.
Video-based feature and what's it?
Yeah. Excellent question. So, I mean, I have a human-centric bias. I'm very interested in actually modeling, these aspects of action anticipations for humans predominantly. But I do believe that some of these approaches and findings will generalize to, for example, certainly humanoid robots. And so, yeah, my student actually is already working on trying to generalize some of these approaches to, for example, simulators of humanoid robots and see whether we can also achieve good results in that context.
Thank you very much, Dr.
Thank you.
Because of time, and we have to move forward. And but if you have any questions, feel free to ask questions on our YouTube channel, and then we have last screen. And so, yeah, now let's welcome next speaker, Dr. Kim Song-Yuan. And let me introduce Dr. Kim Song-Yuan. And he is currently a professor and director in SUNY Buffalo.
Yeah, can online hear me now? Hello? Okay, great. Sorry. Yes, I think. Okay. For example, if you see, I think we see many of the recent results like this, thanks to the modeling of the video language together, right? So it was. Okay, so I'm not. So basically, you can understand the video by leveraging the way we learn from language by aligning visual information with language information, so-called semantic understanding. This has been done successfully in the past 5 years. And also even for video odometry, this video language model can start playing a role as well. For example, instead of quantitative video odometry, of course, you need a precise localization. You can now do quantitative video odometry by using vision language models. Just to play the video and ask the model what kind of the camera movement. It's not going to precisely tell you the location, but it can tell you the camera is moving towards the left, the camera is moving front with what kind of speed, for example. In the beginning, I was kind of surprised to see the good results. The results actually is good, quite reasonable. But later on, I understand, because why I feel a bit confused is because, look, these vision language models, they really do not have 3D projection in its model, in its reasoning. Okay, its reasoning is more in language tokens. However, it still can do a reasonable job by matching the video pattern with the annotated languages. Okay. So the thing I ask myself is that, okay, so language has been a sequence of tokens. It has been very successful to build large language models today. Video is another sequence of visual tokens. Okay, video is certainly a sequence, and we have been successfully seen by modeling video as a sequence tokens, and there's many applications. But would there still be some difference between video and language? So to better answer the question, I try to check the language a little bit. So I find a very unique sentence. Happened to be my colleague. He now is a retired professor. This sentence was coined in more than 30 years ago, now in the natural language community. This is a valid English sentence. What it means, okay, so I come from Buffalo. Buffalo is a city, the big is a location. Buffalo is an animal. And buffalo can be also a verb. This buffalo is a verb. Buffalo, when it serves as a verb, it means bully. Okay, so this sentence simply means there were 3 animals here. Buffalo, buffalo, there's the first buffalo, which buffalo, buffalo, the second buffalo, the first buffalo, which the second buffalo bully, go to bully the third buffalo. That's this sentence literally means. Okay, I send this to GI and it draw the picture. Okay, this AI generated image to illustrate understanding of this sentence. Okay, perfect. So we have a sentence. Every sentence has a same token. It gives compound meanings. Very nice language. However, if I give a video where every image is identical token, would it be a video? That's a question. Okay, so from here, I think I want to say we may have still some fundamental gaps between the language and the video. In video, every frame, the difference is describes motion, but in language, we don't have this characteristic. So then, if you look at the videos carefully, actually, when we talk about video applications, sometimes we do not very much cater to the type of the videos, but different types of videos, they actually have different applications and they require different tools. For example, if you look at the videos, you can categorize the videos into 2 dimensions. One is static camera. A camera never moves. For people in this room, video odometry, those kind of video usually is not too interesting. For example, you have static camera, static objects, image. You're going to have a static camera, but a moving object. That's not for video odometry. That's for video surveillance. You could have a moving camera, but a static scene. Gaussian splitting, nerve, novel view synthesize is for this. And you also, of course, you can have moving camera together with a moving object. Okay, video generation, video odometry, all from that. And if you see those different types of videos, you're going to see each of them convey different information. For example, if you have a static object, static camera, most likely you see the appearance. You may infer depth, but that's not direct. If you have a static camera, moving object, you see the appearance, and you also see the motion. You see how people moves. If you have a moving camera together with a static scene, okay, then you see the appearance together with the geometry. That's a slime, and that's video odometry as well. Location of the camera, you infer that from the video by nature, from your brain. And of course, if you see a moving camera together with a moving object, you see appearance, you see the motion of the object, and you also see the geometry of the scene. Okay, that's everything. Again, video odometry, we care more about the moving cameras, but for other videos, the first row also matter. Then what is really a video? Okay, so video is a sequence of image for sure, but physically, it tells you appearance. What's the color, appearance of the object you see, the motion, how the sense moves, physically change location, the geometry, the shape. Okay, video odometry is highly relevant to that. Together, we can infer the semantics. And do not forget about location. That's the task of the video odometry. Given the video, can you infer the camera location from the video? That's the problem of video odometry. So video as a measurement tool. Today, again, we see many successful applications by either using video language model or using traditional methods. But is it solved problem? Is it that become to a very mature problem? So let's see a video. So you see this, I guess you see a house here, right? And then I can play the video and you can see, you can sense what kind of geometry you sense. You see the house. So far so good, right? You can see the house, I have video odometry, and now my camera moves this way until I move towards right. Until you see something not that comfortable. Until you see the final. How many of you think this is a real video? No one thinks it's a real video? Some, okay. Some hesitate. So let's display it one more time. Human playing video odometry or slime. Okay, I think this angle tells you what exactly the object is. First, it is a real video. This is something in Washington, D.C. I captured this video myself. Whether you're leveraging your visual language model a lot to play the video odometry game like this, I guess could make a difference. Okay, your human prior, the house, by the way, is not a regular house, obviously, right? So it's inside. This corner is not towards the outside. This corner is towards the inside. Okay. Even for human being, this easy thing to very quickly figure it out. So now, again, we know video by nature capture entangled information, geometry, motion, appearance, whatever. So then, and you do not have to, by the way, you do not have to disentangle them today. There were entangled representation, but if we disentangle them, would there be any benefits? For example, help modeling reasoning. One lesson I learned from recent work, this one is in Europe last year, is that actually, for example, for visual editing, you may prefer such a disentangled modeling. We have seen image modeling editing in very popular tools, including your smartphone. For example, what if I want to remove object? Okay, so today it has been very successful, but surprisingly, still some tiny issue that cannot be very well addressed. For example, the shadow. I want to remove this kit, but how to make sure the shadow is moved together? Okay, you can ask image to infer the shadow, but not always successful. Okay, but human being, that's the nature. I mean, when I move the kit, I know that's his shadow. I'm going to remove it automatically. But for the perception side, for the model, how do you convince it knows that? Surprisingly, the problem will become much straightforward if you consider both the appearance and the geometry, which is depth, together. We never see we do not see the shadow on the depth. We see the shadow on the appearance because of lighting condition, right? But what causes the shadow is the geometry. There's a causality, there's a physical causality because of geometry, so that we have the shadow. Geometry, if you model geometry appearance together, surprisingly, you can actually get a better solution to this problem. For example, you have an image, you can infer the depths, and then you can, instead of directly edit the image appearance itself, you can edit the depths first. And then by using the depths, you can render the image again. Then you can naturally address the shadow problem, because when you need to render the image condition on the depths, it can handle the shadow better. So the first thing is that you want to remove the object together from the depths, not from the image first. You remove the object from its depths. And after you get new depths where the object is missing, then you can re-render. Okay, when you re-render with the depths without the object, then the shadow automatically is not going to be rendered in the appearance. It looks a very straightforward approach, as long as you respect that the image is a matrix of pixels, but internally it captures completely two different physical information. Geometry is one, depth, and appearance, the color is the other. These two are highly coupled together, but they're not identical. Then you can see, we're going to see, okay, so you can see not only the shadow, but also reflection, right? So thanks to the geometry, again, the only thing is that think about the image. When you see the image, do not think just as a matrix of pixels. Think about it. Every pixel has a distance towards the camera. It has a depth. Some of the pixels can be caused, for example, shadow and reflection. This is a bird reflection, right? So the mirror reflection, this kind of reflection as caused by the geometry of the object. And this is the shadow. Now, if you can render in the 2-step rather than 1-step, you can do a better job. Of course, motion blurring is still the killing. We cannot completely solve that, but that's another. If you want to better solve that, you may want to model the motion in a separate way as well. This tells how you learn the causality between the object and the shadow. Once you know which cause which, you can do a much better job. Not only single image, but you can, if you can disentangle the geometry with the appearance and using language to drive the rendering, you can do also a better job in terms of the scene rendering, for example. For example, you have a video, you scan this. Of course, you can infer the camera location using your video odometry, and then this is time, right? And then if you want to re-render this, we use iPhone. This one is with Apple. And then you can give a language and say, what do you want to render the scene? Again, you do not want to change the geometry, but you want to change the appearance. The appearance is defined by the language, but not the geometry. Then you can change your room, your 3D in the way that you like, but by keeping the same size, almost same size of your room, which is inferred from the video. Something else, industry, right? So, and you can render the top, the flow, things like that. And you can also consider to generate human motion video. This is skeleton-driven video motion. But if you want to separate the generation by both video and depth, okay, it can do a better job. So what does it mean? So it means we want to. So we see the results. So it means that if I have a skeleton, one single image, I want to use one single image to drive a person moving. I guess now we see many of this such a demo already. But the lesson we learned is that rather than just generate video, if you generate the video and the depth together, it usually helps each other. You generate better. Turns out you generate better video together, better depth, because they can help each other. The depth, geometry, and appearance, they are kind of disentangled, but they also can help each other, right? And then if you want to generate high quality video, that's purely about generation. This is purely about generation. One of the challenges for generating high quality video is that we do not have high quality video data set. We have high quality image data set. But for video, usually it's low resolution. The question is that can you leverage both high quality image and a low resolution video to generate high quality, high resolution video, right? The trick is that, yes, you can, but you need to disentangle the representation of the motion from the appearance. Appearance tells you how good the image look like. The motion tells you how smooth the video will be. So basically, your teacher learns the motion from your video model, low resolution video. You capture the smooth motion, but you learn the appearance by training an adversary from the high quality image to make sure your image in the video looks good. There's conflict objects, but you can leverage distillation to achieve the two goals together. Again, simply means you're going to learn the video generation from the low resolution videos, but they only learn the motion, optical flow, advanced version of the optical flow. And meanwhile, you want to learn the appearance from the high quality image. Make sure both your motion is smooth and also your appearance is nice. I will skip the details, basically diffusion plus adversary learning to achieve both goals. You can achieve faster sampling by almost similar, even slightly better results. For example, if you're willing to separate the motion and appearance, then you can improve the previous method, which teacher needs 50 steps. Now you can achieve only 4 steps, comparable, but much faster. Okay, also with certain good quality because you learn the appearance from the image already. This is another. Again, if you only learn from the low resolution video is nice, but the resolution is usually not. Okay, so now you want to improve the video quality. You want to still keep the motion, but you want high quality image and customize, but depends on which image you want to learn from. This is 2-step is not good enough, but a 4-step can do a quite a more reasonable job. Okay. Okay, so this is the, and then let me see another one. Right. So again, this is the benefits. If you're waiting, this is conditional generation. Again, only 4 steps as well. High quality image. Motion is completely driven by the second. This video are in the high quality image level of the quality. And again, faster sampling speed in diffusion because you couple the benefits from both. Okay. This is the first part in the share. To sum up, the lessons we learned is that although video, in terms of data structure, data science is a volume of pixels. Video is nothing but a 3D volume of pixels. Every pixel is a number. You have the 3D matrix. That's it. You can think about it as a sequence of 2D matrices. You can tokenize it, usually which we do. However, do not forget that video by itself is a capture of the 3D world, is a projection from 3D to 2D. It captures information, physical information from different aspects, not one. Although everything is represented by the pixel value, but internally it captures some physical information. If you're willing to separate them and use them, sometimes it can benefit your performance or your application. The second part I want to share a little bit is about this disentangled representation help location sensitive video generation. I understand that we are in video odometry here. Again, I work much less on odometry. I'm more interested in video. Video odometry is a problem that given the video, I want to know your camera location. Okay. I myself is actually more interested in similar to Professor Lorenzo is somehow more interested in the inverse problem of the video odometry, which means if you give me the trajectory, the camera location, maybe in the future, I randomly draw camera trajectory in the future. Can you generate the video for me? That's the inverse, the kind of inverse problem, video odometry, right? Not from video to location, but from location to the video. This looks more challenging, but with today's video model, we can do something. For example, if you have ever heard about the video explanation in space and time, right? So the input is the past video, right? What I want is a future video, but the future video is not based on the prediction of the trajectory, is based on my pointed out trajectory. I just want to know what if I go this for the next second, what I'm supposed to see. Okay, this kind of counterfactual problem, what if problem as well. For autonomous driving, if you're a driver, that's in your habit. The driver makes a decision not based on what he sees in the highway, for example, right? So the driver is doing the decision based on what he foresee. Okay, he foresee what's going to happen next. If you're driving the highway in high traffic, that's human behavior. We make a decision not only based on what we see now, we also make a decision based on what we believe will happen next, especially in the near future. So this is the, for example, this is way more, I think, demonstrated. They can foresee what's going to happen. They slow down purposely to demonstrate certain capability. For autonomous driving, even you can foresee 1 second. Okay, it can be helpful a lot. Okay, compared with if you cannot foresee. Of course, the challenge is that you have to, you have to understand the scene. You have to have the capability to predict the future. You have to know the geometry. You have to know the video generation. It's not the trivial task. It's everything coupled together. The previous approach, the paper actually worked on this in the beginning from Stanford, is that they use entangled representation. Basically, they encode the video in as we usually do, right? So by entangle the representation, I mean the geometry, appearance, motion are all together in one token, okay, in one representation, and they want to use that to do the novel view synthesis. Again, if you see today's Gaussian splitting nerve, usually they do not separate the geometry and appearance. They just say one network. I can give you both geometry, appearance, even motion. Okay, that's called entangled representation. It certainly works, but whether it has limitation or not, I think it depends on your scenario. So now the simple way we make changes is that, again, we do not really make any, I don't think it's completely novel idea. The only thing is that, let's say, can we respect the physics? For example, you have 3D space, you have time, and you have semantics. Can we get the point cloud, the really 3D geometry first? Can we forecast the ego motion, how your camera is going to move? Can we forecast the object motion in the point clouds? Can we change the point cloud? So meaning you, instead of forecast the video, can you forecast the point cloud first? It's actually possible, right? And then after that, can you render? The learning objective is that you want to make sure when you follow this and you have Gaussian splitting to render the point clouds, okay, you want to make sure that it matches your ground truth. Okay, so you can use this way to render. This kind of render follows nothing but physical, kind of physics of the word. Today we're talking about word model. I mean, when you think about word model, it's nothing but, I think, to me, it's nothing but I say we want to respect the word is 3D. There are some physical laws there. You cannot hallucination, or you cannot assume you can learn everything from your data. If you can, then you may not need a word model. A word is there, physics is there, Newton's law is there. No matter you watch the video or not, you know it. Whether you use it or not, it's your choice. It's like today's Gaussian splitting. When you see Gaussian splitting, when we see the view synthesis, it seems that we never teach the model anything about the disparity. I teach computer vision, I teach my class students disparity. But when I see another PhD student work on Gaussian splitting, it seems they do not assume the model knows disparity at all. The model just see many images and can now view synthesize. Gaussian splitting today can also help to address STEM problem as well. Okay, video odometry. Okay, so we can know the detailed procedure, but again, that's really the procedure. We follow the physics and generate results. It can get you better results. Okay, and also if the most important thing I like is that by following this procedure, if I'm wrong, I know where it is wrong. If I'm wrong, I know whether it is wrong because I predict my 3D point clouds wrong, or because I rendering the RGB image is wrong. It's more transparent pipeline. It can help you to figure out the bug, in a human understood way. Okay, rather than entangled representation, if it's wrong, you have to retune the neural network, everything again. And with good luck, maybe you can find the reason. Okay, so this is some. If you see, if you just use the, and this is the arbitrary future view forecasting. Again, we want to generate the video at an arbitrary location of the camera and at the future time. So this is, if you see this motorcycle is going to disappear, rendered after, blurred after several steps. You could use similar representation to forecast. This is the VR kind of application, but this forecasting, we want to forecast the movement of the hand, not the camera. We want to see how the hand is going to move next. By condition on the location, if you know the camera location in the past, if you can condition that, given the location and then given the past video, you can also help you to better predict where your hand movement, your hand location is going to evolve in the next few frames. And certainty estimation is something this work emphasizes a bit, which I think is interesting because you again, forecasting is never deterministic. You never know precisely what's going to. Everything is possible, but you'd better to have a mechanism to model this uncertainty from your observation to your forecasting. Okay, so I think I want to kind of summarize a bit here. The major message I try to convey here is that again, a video is a sequence of images. I think a few people treat the video as a volume of 3D volume of pixels, because we naturally know we cannot randomly flip the 3D. Time is time, right? You cannot flip into X and Y. That doesn't make sense. Nobody watch video in the other way. is very, however, is very commonly accepted that video is a sequence of images. It is true. Video for sure is a sequence of video, is images. But when we compare with the language, again, we learned a lot from NLP to model a video, understanding event forecasting. I think we have to acknowledge there are still some differences. For example, language is more about discretized symbolic token. Video is more about continuous. When it's continuous, that's of course pixel value is still from 1 to 255, but 0 to 255. But the word, the color is continuous. Language is extremely compressed. Okay, every token can mean something. Video is highly redundant. Every image in the video is almost the same, not identical, but almost the same. The motion captured by the difference between two images are really tiny. You can very well model a semantic unit in the language as a token, but can you easily model a semantic unit in the video as a frame? Is certainly a good question, right? So video and language are not the same abstraction level by default. Language is much more abstraction. That's why it has it's extremely compressed. Then what is video? So video, fundamentally, if you're from the video odometry community, okay, video I think is really a sequential spatial temporal capture. Space depends on your camera. Temporal depends on time. Sequence means it follows time order. It's a sequential spatial temporal 2D recording of the 3D world. We know camera models. We know for computer vision, if you learn computer vision, you know camera models. Image is the projection from 3D to 2D. There are some distortions, by the way. Okay, that's why we need more than one image to get the geometry, get the depth. Language, for the sake of that, the video is different from language. Okay, language does not have that physical law to govern it. At the most, you have to follow the grammar. Okay, you can generate arbitrary language as you want, as long as you follow grammar. But the video is living in the physical world because it's a capture of the physical world. Video is nothing but a capture of the 3D world. And when we talk about the word model, again, if you want to say the video has some relationship with the word model, I think that's because the video is a capture of the word model in both space and time. So video is not just more tokens. Could be more tokens because there are some difference in the reasoning space as well. I think in Professor Lorenzo's talk, he has mentioned some, right? Geometry, motion, location, those kind of things are highly coupled with video. So video understanding often require object prominence, physical causality, and future planning. And most importantly, I think location matters. So when we do video analysis, if you talk to a video analytics person, usually location, if they do not work on video odometry, do not work on robotics, location is less a consideration. Just give me a video, it's a sequence of images. I just follow tokens to process the video. I don't care if my camera moves or not. I do not care whether the video is captured. I don't care how the camera moves over time. Okay, you do not have to care about it, by the way, if you're using video language model today. But would that information be important to you? I think it depends on application. Okay, yeah, without further ado, I will stop my talk here. If you have any questions.
Yeah, any questions?
Thank you.
Question regarding the conversion to extracting the motion information from the video. So if you're saying that you're predicting the motion, then we can just use like polar geometry kind of concepts to find out to warp an image to the next time step. So are you planning to use like CNN to do that, or is it like you are directly predicting the next step without finding the location?
That's a good question. So I think when you say the forecasted video, the motion side depends on two things. Number one, how your camera moves. You have to forecast your camera movement. For example, if your camera never moves, forecast a video, you only need to care about how the dynamic scene moves. That's the second part. So if you want to decouple the video into a physical way, then you may have to model both the camera, you have to forecast both the camera movement, whether it has or not, for example, and if it has, how fast. And also how the scene dynamically change, which is independent of your camera movement at all. That's kind of disentanglement you may want to consider. Again, if you do not consider that, you still can generate the video. for example, using an entangled representation, the video can actually couple these two things together, but it does not mean it is easy control. When you segment the two motions, you can better control your video generation. It naturally gives you the controllability of your video generation. Yeah, so that's the thing. Maybe one of the benefits if you want to generate a controllable video. Yeah. Thank you.
We have time for another question. Actually, I do have a question. Actually, you mentioned about depth as well as appearance, and it seems like that is rendering. Actually, I use the depth for rendering. It seems like it's the worst process of shape from shading. Do you see something like is the relationship and how to use the shape from shadings principle and to support right now what you are doing? Use the shading, use the depth to help you to do the rendering.
That's definitely a good point. So in this talk, I mentioned about the appearance, which is your color of your pixel, the geometry, which is scene of your 3D of your depth of your scene, the motion, which is a physical movement, the location, which is the camera location. But there's one thing I myself was not capable incorporating, which is the lighting.
Mm-hmm.
The video by itself is also completely controlled by your lighting condition. If you change your lighting condition, your video will be different. If you change this light to be darker, you're going to see a completely different video. Okay, so video is the reflection. Another important cause of the video appearance is the light.
Mm-hmm.
And then certainly if there's a way to decouple that lighting, for example, you can infer is ambient lighting or is point lighting, right? So you can model that. If you change that, control that, and that's definitely a more also controllable factor for the video generation and also editing.
Yeah.
Yes.
Great. Thank you. Thank you very much, Dr. Yuan.
Thank you.
Let's move to the next speaker, and Dr. Joe L. Vivas, is my pronunciation correct? Okay. Okay. Exactly. Okay. And Dr. Bills is a research director at NVIDIA and leading our work of team. And his team is the latest advantage of control. Research area includes multiple center and data center, equally of more efficient cable system. So, yeah, Guoyu, can you hear me? Guoyu, can you hear me? Okay. So, yeah,
Okay,
Guoyu,
now
can you hear me?
now I can hear you. Can you share your screen?
Yes, I can. Let me,
Okay. Now, that goes to the last speaker while sharing, and let me introduce Dr. Lantao Liu is a professor in Indiana University at Bloomington, and he's also the founding director for robotics in the Ludi School. His work spans from single robot and multi-robot system with applications in smart transportation, high-speed autonomous racing, remote sensing, and infrastructure. And in Indiana University, Dr. Liu led a team to develop the university's class-school robotics program and helping establish multiple robotic education and research ecosystem. And he has led a team actually winning multiple times and for the racing cars as well. So Dr. Lantao Liu, and you can go ahead to present.
Okay, thanks, Guoyu, for inviting for this workshop. So can you hear me well from your side?
Yes.
Okay, cool. So first, yeah, well, I apologize that I cannot attend the workshop. There are something that I have to deal with on campus, so I'm not in the ICRA either. So basically, to give everyone a brief kind of overview about me and also my work. So I'm more from the robotics side, although I use a lot of computer vision and I do a lot of perception work as well. So today, what I'm gonna do is that I will present a work that covers kind of three different views. The first is about the geometric view, and I will talk about how we can use some abstraction representation to help robots to understand the environment. And then I will talk about the semantic view, where the computer vision plays a lot of a role here. And finally, how can we use those perception models and then combine with the so-called spatial intelligence for helping the robots to do some action in the real world. So, well, a motivation scenario is we are trying to deploy the robots in the real world, especially the outdoor environments. So my group had been working with the U.S. Army Research Lab for last 5 or 6 years. And so the challenge here is that if you want to deploy robots in the wild, where the wild means that it's super unstructured, where typically it's off-road environments, and how can we, how can we develop the autonomy stack so that robots can perform some tasks specified by the Army? There are some evaluation metrics. So what I want to tell here is that the perception is very important. All the teams, they have been working on the full stack autonomy that covers like the perception layers, the decision layers, the motion planning layers, control layers, and also possibly the multi-agent layers. But later on, then many teams figure out that actually the perception as the first layer almost be decisive. So first, I want to talk about the geometric view. How can we deal with geometric representation and still be useful for solving some real world like unstructured navigation? So here is one very classic autonomy stack where the stack has multiple modules. In this one, we use let's say ranging data like LiDAR or radar data, and it's a very typical that the ranging data will be represented as the so-called occupancy map, which now becomes a mapping problem. And then we can derive the so-called cost map,
where the path planner can be built on top, and eventually we can drive robots on in the world. So the video here is from a self-driving scenario on the pretty kind of structured environment, where the point clouds had been represented as the cubes, like yellow color cubes, where the cubes can inflate the size of the point cloud to to represent or to give some safety cushion for the obstacle avoidance. Now, the issue is that if you want to deploy or use that that kind of pipeline, so imagine we deploy our robots in the forest like this. And also we have so many points from a high definition LiDAR. So all the points, if we inflate their size as small cubes in the world, then probably we don't have any feasible or free space left for navigation. So actually, there are lots of drawbacks from the occupancy grid mapping, like how we leverage, or how we convert the point clouds into the occupancy world that can be can fed into the robot's stack. So first, it's very computationally heavy because there are so many points, and also there are also assumptions. And one kind of well-known assumption that they assume that the points are independent, meaning that they don't have spatial relations, and which can be wrong. So in our earlier work, what we want to do that we want to design an abstraction method that can be powerful. So this ring is the Lord of the Rings, which can be very powerful. And I use this picture because as you will see, actually our abstraction model is very similar as this ring type. Let me show that. So the idea is we will have to re-represent the point clouds. And the first step is pretty simple, where we convert the point clouds on a ring-like surface. So the red colors on that representation from the bottom left corner is the raw point clouds, where what we can do that we project all the points on the ring surface on the right side. Where the basic idea is that so we don't throw any data. Instead, we do the projection, where all the points will be put on top of the surface of that ring. So the color maps on the rings represent a range value. And then the location on the ring surface is related to the orientation, or as you see the coordinates, the r, the phi, the theta for the row picture you of that points. So basically, we don't lose any information. We just represent that point cloud in this form. So to proceed, I want to briefly introduce some background, which is the Gaussian process, where a Gaussian process is sort of a kind of interpolation method. If we have some data points, we will have to predict a continuous function line, like function as purple line shown here. And the Gaussian process is powerful not only for interpolation, but also it gives us the evaluation about the prediction quality. And that is measured by the variance or the uncertainty levels. So this means that output from Gaussian process, we have two things. One is the mean value, which is the purple line, which is continuous function. And then the other is the evaluation of confidence about the prediction, which is the variance. And what we can do that we apply the Gaussian process on top of the that spherical or the ring-like that surface. So there is a hurdle, and that is the computational cost. So Gaussian process is known that it's computationally expensive. It's an n-cubic time. So imagine we have thousands or millions of data points every second we received from LiDAR scans, and how can we compute real time to represent that surface, right? And to kind of mitigate that, we use a sparse, sorry, it's not spare, it's called a sparse Gaussian process. This is a typo here. It's also SGP, which kind of abstracts the Gaussian process, all the data points into a smaller subset of points that can best represent the original data sets. So if you can look at the middle picture shown here, the purple dots can be thought as those selected good points that can still very accurately outline the function shape. So we can use that purple dots to represent the entire data set. So if we use that, actually the time is for computation is almost linear. So in this way, then we break the hurdle for the computation. And the Gaussian process will give us two outputs, mean and variance, as I mentioned before. So correspondingly, the mean give us a surface called the occupancy surface, and the color that surface. And you see that surface now becomes kind of continuous. So the missing parts are kind of we manually removed because they are not useful. How we remove that is actually use the information or the cube from the second surface, which is the bottom one. That is the variance surface, which is very useful. And in this variance surface, you can imagine that the white color parts are those high variance or high uncertainty regions, and the black parts are the high confidence or low uncertainty regions. So the way that how we call out or how we remove those portion on this the mean surface is by using the high variance part. It means that if we know this is high variance, it's more likely that there is no data at all, so we can just remove that part. Now with that, so this representation gives us multiple very nice benefits, and the first one is we found the surface, the variance surface bring us a navigation cue directly. This means that actually a good representation from the perception or for the perception can naturally lead to navigation without some other module that we have to design and have to, to kind of optimize. So let me briefly describe the idea, which is very simple. So if you look at this variance surface, this ring, so the white parts are the high variance parts, and the brighter the color, the higher the variance. So what we can do that, if you look at the right side, which is the raw data points, so in fact, the band, this white band, is actually kind of describe that missing portion in that point clouds. And also the whiter the color, this means that the middle or the represent the middle points that has the largest kind of clearance away from those points. And this means that this is very good. We just need to look at this band, this white part band, and seek the brightest part, which means that this can be a good cue for guiding the robot to move toward that direction, which means that it's a free, navigable, and also a safe space to move forward. And here's a demo. So we call this the point that we figured out from that white band called the frontier. And in this way, then we just introduce a new frontier from the frontier family. We call that a GP frontier. And in this demo, we can see that now navigating to this corridor, and so the band or the ring here give us enough cue to where to move. So we can imagine this band as like a dashboard where we chase that white color, that small ball, which are the selected the highest uncertainty points to move forward. So more interesting thing is that so here is a more clustered environment where we have so many cafeteria table and legs, where so those points, as you can see, that they are very messy, right? So if you want to delineate the geometry, it can be very complicated. But the GP, this model, so let's look at that again. So instead of trying to figure out about the geometry, about those legs and those small objects, we look at this dashboard, and the dashboard can kind of lump all those big, small objects together as one chunk of things. Like those, you can imagine that a big chunk of the object field, and the white color is open space between those kind of chunk of these object fields. And this is how we can give the robots a cue to move without focusing or paying too much attention on small, detailed kind of nuance, which are not that important in the navigation. Now, another benefit that we receive is that actually the GP, that's the foundational, not foundation, but the foundation of that framework, give us uncertainty assessment, and that uncertainty assessment can also be used as a second layer from a larger scope of the environment to guide the robot to explore some unknown space. Because exploration of unknown space usually is driven by the uncertainty. If we know somewhere, then it means that we are pretty confident. We don't need to visit more because we already know very well. If there's some space we are not sure, because we want to go there to explore our curiosity to discover. And that curiosity is high uncertainty or low confidence region. And we just use another GP layer on top of that, the local GP, which is the ring. And in this way, then we can also combine with the graphical model, like this is the metric graphical or metric topological representation to outline the navigation traversal, all the regions that we have gone so far. So this topological map actually represents the skeleton about the environments that we have already visited, which represents how we, map. We can imagine this is a topological map for outlining the space navigability features. So let's look at this example. So this is a simulation, and we deploy the robots in this kind of small forest environment, where you see that this ring now is just modeling about the local perception, and that ring guide the robot to move towards unknown space, and chasing that unknown space forward. And also those red points are the like anchor the spatial points that outline the entire this park actually. And so actually, let's see that again. In fact, during this exploration, there are some regions that we see that there are some green colored points. Those are the outlets about the new kind of intersection where we can now explore all the intersection that's outlets, but we just, because these represent very high uncertainty points. So this means that those parts are some next step exploration points that we can come back to visit once we have we finish our other branch of exploration. And that's the key idea for that exploration. And so we tested on the real world environments. So this is actually a small forest near our campus. So in this testing, you can see that this robot now is using that representation model to move forward. And at certain point, there is a fork here. See that there are two branches. And in this way, robots will choose only one branch because it cannot cover two together. And so it marks some branch that, that opening as high uncertain, high curiosity region to be explored once the first branch had been finished. And this is another scenario. You can see that robots is moving in a very narrow space, a narrow corridor. So in this way, then so what I want you to pay attention to that actually the behavior of robots is a safety kind of aware, because it's always chasing the middle point about that narrow corridor. So in this way, that it's also maximize the clearance away from the like the bushes nearby, and this is also behavior that we desire. So we also compare with some other baselines, including the graph-based planner, which had been used from the recent DARPA's Subterranean Challenge. And actually, our method compared with those methods, and we the orange one is our method. So we can sorry, the blue one is our method. So as you can see that so the exploration time, which is stop here, is much shorter than other baselines. And also the variance, you see that across multiple trials, variance is very small. Because this means that so our robot's behavior is not kind of oscillating all the time in the corridor. It's always kind of chasing or aligning with like the optimal middle point of the corridor for the traversal. So yeah. Now, another thing that I want to mention is that actually there are some other benefits we can also use that the dual ring representations. So we can do the reconstruction. What it means is the Gaussian process we use is a sparse version. And what we can do that, we can do the sampling on that sparse representation to recover the dense version. And because Gaussian process is like a functional space-based kind of representation, it means that as that function, any point, you can think that as a Gaussian distribution. It means that we know the mean, we know the variance, and we can sample using that Gaussian. And this is how we represent the how we can do the resampling. So the surface ring on the bottom tell us that which part there should be occupied things, we represent that we should sample, and some other part are empty or free space, you just ignore. And we focus on that like dark regions to sample more densely, and we reconstruct these original point clouds. So if you compare with the original point clouds, and which is the top right corner, so our reconstructed can pretty well kind of align with the original point cloud, right? Now, so this is the third benefit. This means that we can actually the Gaussian process or the sparse Gaussian process can be viewed as like an encoding decoding process, where encoding means we use abstracted version to compress the model into a smaller size model with smaller footprint of memory and also communication. And that smaller version will be decoded back whenever necessary. And with that decoded version, of course, can be used for other downstream kind of module like the occupancy mapping, as what robotics people have used a lot. So here is one example that how we use that. So imagine that we want to do the subterranean challenge. We go to a tunnel or a cave where only robots will be deployed inside, and the human will wait outside. Human will hold a computer, but human want to see what robots maps on board. But the communication bandwidth will now allow robots to pass all the points along to the humans because it's so dense. So in this way, then the encoded SGP will do that with a very, very low bandwidth. So here is the process. You see that when the right side actually is reconstructed version on the laptop held by the human user outside the cave. And it's almost like similar to what the onboard mapping process that is used, as the like fully autonomous, on top of the robots from robots view. So we also tested in the indoor environment, and so this is actually the figure on the top right corner is the final version, and the bottom one is kind of real-time constructed and viewed from the user end. So I will just speed up this video, and so I want to show you the final results. So if you compare between the onboard map versus the reconstructed map from the right side, it's very similar. And the only difference is that there, some corners of the map on the reconstructed might not be that sharp, because again there are some like encoding decoding process, and a certain accuracy might be lost. So this is the basic idea for the geometry analysis. So next, I want to jump to something that is not geometric. So geometric is very powerful for like delineating about the occupancy, and it can also guarantee the safety if we are very careful for the magical things, like say our space is super narrow, then geometry is very important. We have to make sure that we are not touching the environment, touching the obstacle at all. But there are limitations on geometry. So for example, there are so many semantic meanings that if we don't know the meaning, then the navigation might also fail. So let's say the mud. So geometric analysis might show that this mud field is flat, so it's traversable, it's good to go. But mud, it's kind of easily strand robots inside. Similarly as the grass. So the grass can, if it dense grass like this way, from the geometric analysis, it can be like a wall, like it's obstacles for sure, but actually it's traversable because they are soft. And this means that we do want to use the semantic meaning to help us to do the navigation task. So there are some issues that we have to deal with. One is the domain shift, and we need to make sure that our the semantic things will still work in the real world. So we will use a lot of vision for sure. And so here in this scenario, I want to show you about what mean by the domain. So domain can be relevant to the environment. So for example, in this scenario, that there are some like a trained model we got from like a Bloomington on our campus. And if we want to use that model in the urban environment somewhere, and there it might not work that well because the data format is not the same. The data distribution are the same, not the format. And there could be some other like more challenging scenarios, like say the Mars. We don't know how that looks like, but if we deploy that somewhere in the future, and then the shift can be even bigger, maybe. In this way, then we need to figure out about like the so-called transfer learning, how to transfer knowledge from one model to another one, and still work very well. So why we want to do that? Because in our mission, like I mentioned, that from the Army's perspective, they want to deploy robots in the wild. And the issue for them is that don't have data. So there are so many data that people collected from like urban environments, from self-driving scenario or some others, or small device data set they curated from their campus or whatever, but they might not be applicable to other so many diverse and challenging outdoor environments. In this way, then so we can train a model from some data set we have where it might be labeled, but if you want to deploy it there somewhere for, like say, very challenging outdoor environments, we don't have label. So we have to find a way to use the knowledge that we learned from somewhere to apply that to the new environments. So the domain shift can be like from simulation to the real, sim to real. It can also be from, like I say, some weather or some seasonal facts, or from like the lighting conditions, or different types of factors can cause different domains shift. And of course, it can be like the cross shift, like say from simulated city to a full forest. So it can be a very different type of the shift. Now, from our groups, we have been trying to different ways, including about using designing some model to bridge that shift, and also do some data bridging as well. In this talk, I will just focus on the model part. So, to be concrete, actually, I want to give you some people a very brief background what it means by the like a domain shift, and also the task relevant kind of specifications. So assuming that we have the domain and a target, two domains, sorry, the source and target, two domains. So source can be, it can be from some known data sets where we have the original data, and also the ground truth labels, where the ground truth labels can be different classes. We call it semantic classes. It can represent different objects, like you see from the bottom, that's the panels. And for target application, the domain might have no annotation. Then how can we apply that to learn a model to predict what those kind of the segmentation meanings or classes in this new target application? Now, actually, this does matter. So before we go to the technical details, I want to show you the results to give everyone some high-level idea. So if you look at the RGB, this is the first column, it's RGB. And then without domain adaptation, so we transfer to other scenario. And so you can see that actually the prediction is pretty bad. So you see this is a concrete floor, but you already kind of predicted multiple things there. With the domain adaptation, the result can be much smoother. It's more consistent for the outcome. And the second is on the outdoor environment, where you can see that without again, there's a consistent issue, and also the wrong kind of the prediction. And then with adaptation, so you see that the sky can also be seen, and the result can be much better. So from our group, so we started working on the vision part like since a couple years, probably 5 years ago, and we kind of evolved also a lot based on our own observation and experience. So the key idea I want to mention is that so in general, we started working on purely on the like understanding the environment meaning or the semantics first, and then use that outcome to connect to some autonomous stack modules and for robot navigation. Later on, we figure out that actually we should kind of evolve the entire that semantic understanding, also including about like the context aware, like traversability analysis. And later on, then like from last year, we started working on the goal condition, like a more robotics conditioned planning and control strategy into the entire like a general integrated framework. So I will break it down that into the with some very simple kind of high-level description on those efforts. So first, let's look at the from the segmentation perspective. Now, the first one I want to talk about is called the CALI. The idea is, well, the CALI means it course to find alignment based the unsupervised domain adaptation. Here is the background. So there is something called a domain alignment, where it means that if we have two domains, you can imagine that we have those are features, okay? The circles are features. And the left one is the source domain, and the right side is the target domains. And the goal is that we want to merge the two columns together so that they represent the features retrieved from the source and target. They are kind of domain invariant. And to deal with that, early stage, the researchers had used like the adversarial alignment strategy to something like the GAN framework to train, to merge, to retrieve some those domain invariant features so that the discriminator cannot differentiate. However, so if you look at only about the domain alignment, we want to merge the two columns together. As you see that there are two scenarios as outcome. The middle one, they are good because you see the two domain merged, but the classes, okay, the class like the color now matter. They can still be separated out. But on other way, if we don't do very good job, the classes can be messed up. So this is something that is wrong. But we want the domain to be domain invariant, but also we want to separate out different classes because this is our eventual ultimate goal for do the segmentation. And to do the class assign to separate the classes, there's something called the class assignment, and this is the adversarial kind of the training framework. The key idea, well, it's actually very simple as well, and it's you need to use two classifiers where the generator will try to create to generate the features so that the two classifiers cannot differentiate between the two domains. Well, from the classifier from the last scenario, the discriminator scenario perspective, it will try to maximize the difference between the two classes. So the key idea here is that there are some boundary classes as shown in the diamonds, those samples. This means that those are critical. Well, only if we put those boundary ambiguous those features inside some well-clustered fields or those regions, this means that those classes can be well defined and also be learned. And this way, then the two classifiers will try to maximize discrepancy. And this means that they are trying to expose those diamonds, those features out as much as possible. So the two kind of adversarial, these kind of the two things, they will kind of optimize back and forth. Eventually, that's we can generate something that are acceptable. So from our side, because this is the adversarial framework, and one kind of issue that people have figured out that is the training stability issue. This means that well, at the early stage, the generator can dominate. This means that the discrepancy can decrease until some point, and as that point that we call the inflection points, and then it will turn where the classifier will dominate. This means that the discrepancy will increase again, and this causes the training unstable. So what we want to do that we want to get a curve that is good to describe up to be kind of stable enough and also kind of eventually convert to some optimal or close to optimal points, and that's what we propose. So in fact, the key idea that we design a framework called a pseudo trilateral game structure, which will combine both the domain alignment and also the class alignment together. So the domain alignment will to both on the two sides, two legs, both are adversarial training, and so the two adversarial training will be alternating as a loop, and the two alignments will not compete. And so this design is we call the coarse to fine alignment. So first, the domain alignment will be dominating, and it will give some guidance for later on to better train the class alignment. And there are different focus during that process. So so there are some the good thing that's from our observation we can see you see the inflection point from the like this class assignment alignment. The blue curve has inflection, but from our design, actually you see that that inflection is gone and it's pretty smooth. Now we tried our method on different scenarios. So this one is show about the qualitative results that we apply that framework on the data set. We transfer from the GTA5 data set and transfer to the cityscape. So I usually focus only on the last three columns because they are kind of the real important performance reflections. So the last second column is our method, and the last one is ground truth, and then this last third one is class alignment. If we compare, actually the Cali is closest to the ground truth. So even the class assignment with a strong baseline, you see there are some inconsistency in many portions. So we tried in outdoor environment as well, also with the transfer scenario with the different domains. So again, if you look at the three columns, in the last three columns, you see that actually the Cali is closer to the ground truth. So I'm not spending too much time looking at the details. And quantitative results. So actually, we compared those different semantic classes and also compute the final average, the MIOU. So compare with the baseline. So actually, the margin is pretty big. So ours is like 42.91 compared with the 30 something. So that there's it's like a margin of like a 10 on average. So now with that, well, later on, we kind of evolve further. So we, since like 3 years ago, we found that the entire community has emerged from like adversarial field to like a self-supervised fields. And so there are some very kind of exciting framework existed, such as this one is called the DA farmer. I think some speaker involved in that authorship of that paper as well today. And we also have the second one. This is the HR, the high resolution domain adaptation, and also the MIC, which is a masking image consistency framework. So those are all the self-supervised framework and shows a very strong kind of baseline. So from our work, we kind of extend the high resolution domain adaptation and try to further extend the performance or further augment the performance. We define something called attentive feature refinement domain adaptation. And this is a plug and play refinement module which can be applied on any other like the self-supervised domain adaptation framework. So there are some modules inside. I don't want to spend too much time in it. So the motivation that we want to design this is because that's, for example, in the baseline framework, so they use two lines to like two kind of channels for the final kind of the learning, where one channel is about the like global context learning, and then the other line is kind of local kind of feature refinement learning. And we found that their interaction between the two channels are not strong. Instead, from our design, we want to leverage about the global context and also local feature or local refinement together. And the idea is pretty, I would say, analogous to the common filter, where if we have like uncertainty from different channels from the perception like those models, and how much we want to trust that channel. And in this way, then so the global and also local will be leveraged based on the expected kind of we call the confidence score from their evaluations. And so we compared our method with different baselines, and also actually the column that I'll show here, those are small objects like a person, riders, compared with some other like buildings and also those trees. The small things are kind of the, I would say, a key performance reflector because they are hard to refine or delineate. And we show that in those small things, our method are better than the baseline. And so I don't want to spend too much time here. And so qualitative results. So there are some details we want to we kind of zoom in for us to kind of focus on. So we apply our AFR, the attentive feature refinement model, on those different state-of-art method like HRDA and also the MIC, and show that there are some we are both consistent and also the results are the MIOU are also good. So I'm skip this one. And so here's a video demonstration where actually this is not from robots. This is from a camera video that we are just apply that segmentation framework to see how that segmentation results looks like. And so yeah, qualitatively, I think it's pretty good. So later on, so here we apply the framework by combining with I know that I'm running out of time, but I will finish that within the next couple of minutes. So we applied that segmentation results with the downstream motion planner and controller. So the thing that we can use is the results from that segmentation results can be converted as the navigable space, like the white-black color, so navigable versus navigable. And then we can retrieve some high-level cues from the space, like where is the goal want to go, and then derive some local planner controller to navigate. And the results is pretty good in different environments. We show that it works in both the indoor and also outdoor setups. And so next, we want to extend that segmentation to the traversability. So that's what we found, that actually, if we just connect different modules together, there could still be some discrepancy. Instead, we want to derive that traversability directly from that, that entire supervised learning model. And what we do that, we want to get the prediction on the traversability map, where so the ideal scenario is that near horizon thing, we want to get some high score for navigation guidance, and then far horizon can be like a low score. And also depending on the distance from obstacles, like a near obstacle, we want to like reduce the score to penalize or to guide robots to avoid that obstacle in reactive behavior. And so in this way, then we get a different head from that segmentation. The low level, is the global level, low resolution logic. And so in this way, then this is how we retrieve that feature. So this here is an example that how we showed how that works in the real world. This is indoor. So the traversability map is on this top right figure. You can see that actually the warmer color is more traversable, and then the colder color is it's non-traversable. And so that traversability map can be augmented or elevated into a so-called 2.5 dimensional grid map. And then we can apply the some planner controller that we developed from other, my group, from other authors, that can be, used for complete the entire stack. And here's the outdoor kind of running. All right, and this is even more challenging outdoor in the small forest trail. And we can see that the second one, segmentation, the third one is traversability, and then navigation behavior is also the last panel. So the final one, this is really final one, 2 minutes, okay. And then so we want to further extend the traversability by adding the ingredient about the goal conditioned behavior. In this way, so we want to create something called value-guided navigation. This means we want to also learn the cost-to-go map, which can directly output some policy that guide the robot to move in that environment. And so this is the ongoing work. So actually, I don't want to spend too much time, but the key idea is that actually there is still a self-supervised learning framework. We have a teacher model, student model, and teacher signal is by using the grounded SAM, the second segmenting anything model. And also we combine with some like a symbolic, the AI method, like a Dijkstra planner inside for training. So we get the supervision signal for the traversability map and also the cost goal map. And they are learned it's by the students. And in this way, then let's see the final demonstration. So here is a simulation that we showed in the outdoor, like a forest environment. And so the 4 panels, so this traversability map, and then the last second one is the cost goal map, and the final one is behavior. And the indoor environment. So let's see how the robots will navigate and avoiding the obstacles. I think pretty reactive. And finally,
Dr. Liu,
yeah.
Not is coming in 3 minutes, and so we might need to finish in the next couple minutes.
Okay, that's good. That's actually my last slide. So this one is showing the outdoor environment. Yeah, and so actually the behavior is pretty good. Actually, these results are just obtained from my students this morning. So this is very fresh. So yeah, embrace the future. Embrace the future. So there are some things that we have to think how we should go for next or future steps. For example, there are some balance between geometry and semantics. How can we combine them together? And also for navigation in outdoor environments, we always want to be like a safe. And how can we leverage uncertainty? And so this can be combined with the traversability map and eventually the cost map eventually. And so there are some other speakers already mentioned about, there are very exciting direction in the VOM, VLA, and the world models, and also recently the robotics foundation models. Those are very, I would say, very kind of promising direction that can be combined with all those different ingredients. So I would say that's a lot of things that we can explore. And hopefully there are many cool things that can be discovered very soon in the near future. And that's my talk. Sorry for running a little bit longer. So I hope that I can still have some time for taking one question maybe.
Actually, another workshop is already here, and maybe Dr. Liu, we don't have much time really for the questions, and but audience feel free to email the questions to Dr. Liu. Sorry about that, Dr. Liu. Yeah.
No problem. Sorry for that. I need to watch my time a little bit. Yeah. So if there are any questions, feel free to email me, and you can search my name, and then my website has my email address there.
Okay. Yeah. Thank you very much. That ends up the morning workshop on visual odometry and the localization. I know another workshop is there, and so yeah, thank you.
Thank you very much.